The space between stars is far from empty. By the end of this journey through 30 unsolved mysteries, you will understand why this faint cosmic fog controls the fate of galaxies and the birth of stars. Stretching across light years, the interstellar medium is a vast, diffuse environment filled with gas, dust, cosmic rays, and magnetic fields. Despite decades of study, it hides profound puzzles that challenge our grasp of galaxy evolution, star formation, and the very physics of matter under extreme conditions. Why are there mysterious spectral lines that have remained unidentified for over a century? And where is half the universe's ordinary matter hiding? What secrets do you think the void between stars still keeps? That faint fog between the stars is made of something far more mysterious than simple empty space. The interstellar medium is filled with tiny grains of dust, and these particles profoundly change the light that passes through them. They scatter and absorb starlight, making distant stars appear fainter and redder than they really are. Astronomers call this interstellar extinction, and it is one of our main tools for studying the dust itself. But when you try to figure out exactly what these grains are made of, things get surprisingly uncertain. We have a good general picture. The dust seems to be a mixture of silicates, similar to common minerals found on Earth, and carbonaceous materials, which are carbon-rich compounds. There are also ices, mostly water ice, frozen carbon monoxide, and methane, coating the grains in colder, denser regions. But the precise recipe, the exact ratio of these ingredients, their sizes, and their shapes remain a puzzle. The grains are incredibly small, typically just a few tenths of a micron across, smaller than the width of a human hair, but even that size range is debated. Some models suggest a mix of very tiny grains and larger grains, but observations keep challenging those ideas. Why is this so hard to pin down? Because we cannot grab a sample and bring it into a lab. All our information comes from how the dust dims and reddens light passing through it. By measuring the light from a star at different wavelengths, we can create an extinction curve, a graph that shows how much light is blocked at each color. That curve has a distinctive shape with a mysterious bump near ultraviolet wavelengths. That bump was discovered in the 1960s and is sometimes called the 2175 angstrom feature. It is a clear signature of something in the dust, but its exact cause is still debated. The leading idea is that tiny carbon-based particles, something like graphite or complex organic molecules, are responsible. But no single lab analog perfectly matches the observation. So we have this beautiful clue with no certain explanation. On top of that, there are unidentified infrared emission features. When certain regions of space are heated by nearby stars, the dust glows in infrared light, showing a series of emission bands that do not match any known molecule. These bands are often attributed to polycyclic aromatic hydrocarbons, large flat molecules of carbon and hydrogen that float in the interstellar medium. But the exact family of molecules, their sizes, and how they are formed remain unknown. Every new observation seems to add more complexity, with subtle variations in the band shapes that hint at a rich, evolving organic chemistry. Understanding this dust is not just a curiosity. It is essential for understanding star and planet formation. When a cloud of gas and dust collapses to form a new star, the dust grains clump together and eventually grow into the building blocks of planets. The composition of that dust determines what kind of planets can form and what elements are available for life. Dust also protects molecules from being destroyed by ultraviolet light, allowing complex chemistry to happen in the cold, dark regions of space. So the mystery of what the dust is made of is directly connected to where we came from, and this is only the beginning of the story, because these tiny grains are not just passive particles sitting in space. They are actively shaped by the environment around them, shocks from exploding stars, radiation from hot young stars, and gentle collisions between grains all change their size and composition over time. The dust we see today has been through a long and violent history, so the next question becomes, how do these grains survive and what happens when they evolve? 100 years ago, astronomers first noticed something strange in the light from distant stars. When they spread that light into a spectrum, a rainbow of colors crossed with dark lines, they saw dozens of absorption features that did not match any known atom or molecule on Earth. These ghostly fingerprints became known as the diffuse interstellar bands, or DIBs for short, and they have remained one of the most stubborn puzzles in astrophysics ever since. Even now, after a century of observation and laboratory work, we have only identified the carriers of a handful of these bands. The vast majority remain completely unknown. What makes this mystery so compelling is that these bands are not rare. They appear in the spectra of nearly every star whose light passes through a significant amount of interstellar material. They are strongest when the line of sight goes through dense clouds, but they also show up in the thinner gas between those clouds. That tells us the carriers are widespread, common, and stable enough to survive the harsh radiation of space. So why can't we figure out what they are? The problem is that these spectral features are broad and diffuse, hence the name, which makes them hard to match to any known molecule in a laboratory. Most molecules produce sharp, crisp lines, especially at the low temperatures of interstellar space. But these bands are smeared out, suggesting they come from large, complex molecules that have many vibrational and rotational states, blurring the lines together. The leading candidates are carbon-based molecules, particularly long chains of carbon and hydrogen, or even cage-like structures called fullerenes. One such fullerene, the buckyball, which is 60 carbon atoms arranged in a soccer ball shape, has been identified as a possible carrier for a few of the bands. But that is just the tip of the iceberg. Observational clues point to the DIB carriers being associated with the diffuse gas in the interstellar medium, not with dense molecular clouds or with the dust grains themselves. Their strengths correlate with the amount of neutral hydrogen and with the reddening caused by dust, but not perfectly. This suggests they are a distinct component of the interstellar medium, perhaps a population of large organic molecules that float freely in the gas phase. Laboratory astrophysics is making slow progress. Researchers shine lasers at cold, trapped molecules and compare the resulting absorption spectra to the interstellar bands. It is painstaking work. One molecule at a time, one candidate at a time. They try to find a match, but the number of possible molecules is enormous. Even with advanced computer models, the search feels like looking for a specific grain of sand on a billion beaches. Yet the stakes are high. Identifying the DIB carriers would give us a powerful tool to map the chemical complexity of the interstellar medium. These bands could serve as tracers of organic chemistry across the galaxy, helping us understand the raw material available for forming planets and eventually life. Every new identification would be like adding a new color to our palette for painting the cosmos. So this mystery is not just about satisfying curiosity. It is about unlocking a hidden molecular inventory that exists between the stars, and that inventory is tied to another great puzzle, one that involves the very substance of the universe itself. Where is the ordinary matter, the atoms and molecules that should make up stars, planets, and everything we can see? Because when we add up all the visible matter in galaxies, we come up short by a factor of 2. That missing matter, the so-called missing baryons, must be hiding somewhere in the thin gas that fills the space between galaxies. And the same techniques that help us study the interstellar medium might be the key to finding it. For decades, cosmologists have been hunting for half the universe's atoms. When we add up all the stars, planets, gas, and dust we can see in galaxies like our own Milky Way, we get only about half the ordinary matter that theory says should exist. Ordinary matter means the stuff made of protons and neutrons, known scientifically as baryons. The Big Bang and observations of the cosmic microwave background give us a precise number for how much of this matter was created. Most of it should still be around, but when we tally up the visible inventory of galaxies, we keep coming up short. This is the mystery of the missing baryons, and it points directly to a hidden component of the interstellar medium and the space beyond it. The leading idea is that this missing matter is hiding in a hot, diffuse phase that is incredibly hard to detect. It could be spread across the vast spaces between galaxies in a region called the circumgalactic medium, which surrounds each galaxy like a faint halo. This gas is heated to millions of degrees by shock waves from supernova and by the energy released from supermassive black holes. At such extreme temperatures, hydrogen and helium atoms become fully stripped of their electrons, so they emit almost no light in the visible range. They only glow faintly in X-rays. Detecting that X-ray glow is like trying to see a single candle flame flickering in a stadium full of fog. The gas is so tenuous that its signal gets lost in the background noise of space. So astronomers have turned to a clever technique using absorption lines. When a bright source, such as a distant quasar or a gamma-ray burst, shines through the hot gas, the gas imprints its signature onto that light, even if it is too faint to see on its own. By looking at the spectra of these distant sources, researchers have found tantalizing traces of highly ionized oxygen and other heavy elements, which suggest the presence of the missing baryons. Still, the total amount of matter detected so far does not fully close the gap. Observations from space telescopes like Chandra and XMM Newton have mapped some of this warm, hot intergalactic medium, often called the WIM, but its distribution seems patchy and difficult to pin down. Part of the challenge is that the WIM is not uniform. It forms a vast cosmic web, a network of filaments that connect galaxies and galaxy clusters. The densest parts of these filaments are where the missing matter may be concentrated, but even there the density is only a few atoms per cubic meter, far thinner than the most perfect vacuum achievable on Earth. Finding it requires stacking data from many lines of sight and using statistical methods to tease out the faint signal. This puzzle is deeply tied to how galaxies form and evolve. When starbursts and supernova explosions blow gas out of a galaxy, the material is heated and ejected, only to slowly cool and fall back in billions of years later. This cycle of feedback shapes the galaxy's growth. The missing baryons are essentially the gas caught in that cycle, temporarily too hot to see but still present in the cosmic neighborhood. So the hunt for these atoms is not just a game of cosmic hide and seek. It is a fundamental test of our models for how matter assembles in the universe. And the next step may come from improved X-ray observatories or from new simulations that can predict exactly where to look. But there is another puzzle tied even closer to home, one that involves the very structure of the gas in our own galactic backyard. That mystery concerns the huge, hollow cavities carved out by ancient explosions, and the strange high-velocity clouds that rain down from the depths of space. Some of the most energetic particles in the universe go unnoticed as they zip through our galaxy. These are cosmic rays, a constant rain of high-speed protons, atomic nuclei, and electrons that barrel through the interstellar medium at nearly the speed of light. Though invisible to our eyes, their effects are profound. They ionize atoms as they pass, stripping electrons away and driving chemical reactions that would not otherwise occur in the cold depths of space. Without cosmic rays, many of the complex molecules we find in dense clouds would not form. Yet where exactly these particles come from remains one of the great unsolved puzzles of astrophysics. The leading idea points to supernova remnants, the expanding shells of gas left behind when massive stars explode. These shock waves act like natural particle accelerators. Each time a charged particle crosses the shock front, it gains a little energy, bouncing back and forth like a ball caught between two moving walls. Over time, this process, called diffusive shock acceleration, can boost particles to enormous energies. Observations of gamma rays and X-rays from supernova remnants strongly suggest that they are factories for cosmic rays up to a certain energy, but past a specific point, a mystery appears. When astronomers measure the spectrum of cosmic rays, that is, the number of particles at each energy level, they see a clear break known as the knee. Below that energy, the spectrum follows one smooth curve. Above the knee, the curve steepens, meaning far fewer particles reach those higher energies. Something changes. Perhaps the particles can no longer be confined by the magnetic fields of the galaxy, or perhaps a different class of sources is needed. The highest energy cosmic rays are the most extreme. They carry more energy than any particle produced in human-built accelerators, comparable to a baseball moving at high speed but packed into the size of an atomic nucleus. Their origins are hotly debated. They may come from active galaxies with supermassive black holes, from gamma-ray bursts, or from some entirely unknown exotic process. Because these particles are electrically charged, they are deflected by magnetic fields as they travel. Their paths are bent and twisted, making it nearly impossible to trace them back to their birthplace. A cosmic ray could wander through the galaxy for millions of years, bouncing between magnetic field lines before eventually reaching Earth. By the time we detect it, all memory of where it started is lost. Magnetic fields play a central role in this mystery. The interstellar medium is threaded with weak but pervasive magnetic fields, typically a few millionths of the strength of Earth's field. Even so, they are strong enough to grip charged particles, forcing them to spiral around the field lines. This confinement keeps lower-energy cosmic rays inside the galaxy for a long time, allowing them to accumulate and influence the chemistry of molecular clouds. Higher-energy particles, however, can escape more easily, leaking into intergalactic space. That leakage explains part of the knee, but not the full story. The precise shape of the cosmic ray spectrum holds clues about how particles are accelerated, how they propagate, and what sources are responsible across different energy ranges. And it ties directly to the structure of the interstellar medium itself, because cosmic rays interact with the gas and magnetic fields in a constant dynamic dance. How they deposit energy, drive turbulence, and even shape the very clouds that give birth to new stars is a story still being written. A magnetic field so faint it would barely move a compass needle on Earth sculpts the entire interstellar medium. These fields are everywhere, threading through every wisp of gas and every cloud of dust, yet they are almost impossible to measure directly. Their presence is felt in the way starlight becomes polarized, in the way cosmic rays are channeled along invisible highways, and in the way entire clouds collapse or refuse to collapse. Understanding these fields is essential to almost every other puzzle we have discussed, but they remain one of the most difficult things to study in all of astrophysics. The challenge starts with the instruments. To measure a magnetic field in space, astronomers rely on three main techniques. Polarization is the most common. When starlight passes through a cloud of aligned dust grains, the light becomes preferentially oriented in one direction. That orientation reveals the direction of the magnetic field, because the dust grains themselves tend to spin and align with the field. But this tells us only the field's direction, not its strength. To get strength, researchers turn to the Zeeman effect, a subtle splitting of spectral lines caused by a magnetic field. Only a few atoms, like neutral hydrogen and certain molecules, show this splitting noticeably, and the signal is incredibly weak. It often takes hours of observing with the world's largest radio telescopes just to detect it in the densest cloud. The third method is Faraday rotation. When polarized radio waves pass through a magnetized plasma, their orientation rotates by an amount that depends on the magnetic field strength and the density of charged particles along the line of sight. By measuring this rotation for many distant sources, astronomers can map the field's strength and structure across the galaxy. Each technique gives a different piece of the puzzle, and none of them are easy. What these measurements reveal is a field that varies wildly from place to place. In the diffuse gas between spiral arms, the field is relatively uniform, lying mostly parallel to the plane of the galaxy. Its strength is about a few microgauss, 1,000,000 times weaker than the field at Earth's surface. But inside dense molecular clouds, the field can be hundreds of times stronger, often tangled and twisted by the motions of the gas. Some regions show fields that run perpendicular to the long axis of a filamentary cloud, while others show fields that are aligned along the cloud. This variation is a clue to how the field interacts with the gas, but it also raises a fundamental question. How did these fields get there in the first place? The origin of interstellar magnetic fields is a deep mystery. One idea is that they are primordial, meaning they were generated in the early universe and then amplified as galaxies formed. Another idea is that they are generated locally by a dynamo process, similar to the way Earth's core generates its magnetic field, but on a galactic scale. The dynamo would require turbulence and rotation in the interstellar medium, both of which exist, but the details are poorly understood. Observations show that the field in our galaxy's spiral arms is aligned with the arms themselves, suggesting some kind of large-scale order. Yet the field is also full of small-scale fluctuations, like ripples on a calm lake. The alignment with the spiral arms might be caused by the field being dragged along by the rotation of the galaxy, or it might be the field that actually helps shape the arms. Causality is hard to untangle. This leads directly into one of the biggest unsolved debates in interstellar physics. Is the interstellar medium controlled more by magnetic fields or by turbulence? Both are powerful. Turbulence, the chaotic churning of gas at all scales, provides pressure that can support clouds against gravity, mix different chemical species, and trigger star formation by creating dense pockets. Magnetic fields provide tension, like rubber bands stretched across space, that can resist collapse and guide the flow of gas. Which one wins depends on the strength of the field relative to the turbulent motions. If the field is strong enough, it can suppress turbulence and force gas to move along specific directions. If turbulence is stronger, it can tangle and twist the field, making it less effective at resisting gravity. The ratio of these two forces, called the plasma beta, varies enormously across the interstellar medium, and no single value applies everywhere. Some regions appear dominated by magnetic fields, others by turbulence, and most are in a delicate balance. The mystery deepens when you realize that these two forces are constantly interacting. Turbulence can amplify magnetic fields by stretching and folding them. Magnetic fields can dampen turbulence by providing a restoring force. The outcome of this dance determines where stars form, how fast they form, and how many form. It also affects how cosmic rays propagate, how supernova remnants expand, and how the galactic fountain circulates gas. We are only beginning to develop numerical simulations that can capture this complex interplay, and they often produce different results depending on the assumptions made. Observational tests are rare because measuring both the magnetic field and the turbulence in the same region is extremely difficult with current technology. So the question remains open. Do we live in a universe where magnetic fields are the silent architects of cosmic structure, or where turbulence is the ultimate ruler? The answer may come from new telescopes sensitive to polarized light, from high-resolution observations of nearby star-forming regions, or from the next generation of simulations. Until then, every measurement of a twisted field line or a polarized grain brings us one step closer to understanding the invisible forces that shape everything between the stars. And that understanding is critical because the magnetic field is not just a passive backdrop. It is an active participant in the story of star birth, galaxy evolution, and the very chemistry of the interstellar medium. What happens, for instance, when that field meets the coldest and darkest clouds in the galaxy? the places where molecules grow complex and stars begin to stir from their slumber. Turbulence is the chaos that breathes life into the interstellar medium. If you could somehow fly through space inside a drifting cloud of gas, you would feel it buffeting you from every direction, like a storm at sea but on a staggering scale. The gas is not still. It churns with motions that can be 10 times the speed of sound or even faster. These are supersonic flows, faster than a jet fighter, and they are happening across distances from a few times the size of Earth's orbit all the way up to hundreds of light years. This is interstellar turbulence, and it shapes nearly everything that happens between the stars. At first glance, you might wonder why a chaotic jumble of gas matters. But turbulence is the engine that mixes different chemical elements together. When a massive star ends its life in a supernova explosion, it scatters newly forged metals like carbon, oxygen, and iron into the surrounding space. Without turbulence, those heavy elements would stay in a thin, dense shell, never reaching the distant gas clouds that will eventually form new stars and planets. Turbulence stirs that enriched material into the wider interstellar medium, ensuring that future generations of stars are born with a richer chemical palette. It also dissipates energy. The large-scale motions of the gas gradually cascade down to smaller scales, like a whirlpool breaking into smaller eddies, until the energy is finally turned into heat. That heat radiates away, helping to cool the gas and make it dense enough to form stars. But the most dramatic role of turbulence is in star formation itself. Turbulence creates density fluctuations. Think of it as a cosmic blender throwing clumps of gas together. In some regions, the gas gets compressed so much that gravity takes over and pulls even more material inward. Those dense little pockets become the seeds of new stars. Without turbulence, a molecular cloud might sit quietly for billions of years, never collapsing. Turbulence provides the initial push, the spark that turns a placid cloud into a stellar nursery. Yet the same turbulence can also prevent collapse. When the motion is too violent, it tears clouds apart, creating a delicate balance. Too little turbulence and nothing happens. Too much and everything disperses. The right amount is what triggers the birth of stars. Despite its importance, the origin of interstellar turbulence remains one of the big unsolved mysteries. Where does all that chaotic energy come from? The most obvious suspects are supernova explosions. Each supernova injects a huge amount of kinetic energy into the surrounding gas, sending shock waves rippling out for dozens of light years. Over the life of a galaxy, countless supernova could sustain a turbulent state, but there are other candidates too. Stellar winds from hot, massive stars blow continuously, pushing and stirring the gas around them. The rotation of the galaxy itself produces shear, a sliding motion between adjacent layers of gas which can generate turbulence like a cosmic mixing spoon. And there is even evidence that the accretion of gas from intergalactic space, the slow infall of material onto the galaxy, might contribute. The problem is that we cannot easily reproduce these conditions in a laboratory, and computer simulations struggle to span the enormous range of scales involved. The largest turbulent eddies can be 100 light-years across, while the smallest dissipative scales are a few astronomical units, the size of a planetary orbit. Simulating both extremes at once is currently impossible with any computer. Observations add another layer of complexity. When astronomers measure the motions of gas using Doppler shifts in radiospectral lines, they find that the turbulence follows a specific pattern, a power law that relates the speed of the gas to the size of the region. This pattern is similar to what we see in Earth's atmosphere, but the exact shape of the law holds clues about the driving mechanism. Some models suggest that supernova create a steeper pattern, while galactic shear produces a shallower one. By comparing observed patterns to simulations, researchers try to infer the dominant source, but the data is noisy. Different regions of the galaxy show different patterns, hinting that multiple drivers are at work, and their relative importance varies from place to place. So the mystery remains. This turbulence directly influences the next great puzzle of the interstellar medium. How do molecular clouds actually form and survive? These clouds are the factories where stars are born, and they are threaded with the very same chaotic motions we have been discussing. Turbulence does not just stir the gas. It sculpts it into filaments, long, thin strands that snake through space. Inside those filaments, gravity begins to pull material together, forming dense cores that eventually ignite into protostars. Understanding turbulence is therefore the key to understanding the entire star formation process. And as we will see, these molecular clouds themselves hold a secret, a faint, pervasive glow that reveals the hidden thermal history of the galaxy. The most abundant molecule in the universe is almost impossible to make in empty space. Hydrogen molecules, two hydrogen atoms bound together, are the essential fuel for star formation. Every star you see began its life inside a cloud where molecular hydrogen dominated the gas. Without it, gravity would have nothing to grab onto, no dense core to collapse, no nuclear fire to ignite. Yet if you simply mix two hydrogen atoms in the near vacuum of interstellar space, they almost never stick together. They need help. They need a surface to meet on, a tiny grain of dust to serve as a cosmic matchmaker. The process is called catalytic formation, and it is one of the most fundamental chemical reactions in the universe. But here is the mystery. We do not know exactly how fast it happens. The rate at which hydrogen atoms land on a dust grain, find each other, and form a molecule depends on the grain's size, its composition, its temperature, and the density of hydrogen atoms around it. All of those factors vary wildly across the interstellar medium. Some grains are covered in ice, some are bare carbon, some are silicates, some are warm, some are only a few degrees above absolute zero. Each type of grain may catalyze the reaction at a different efficiency, and we have only a handful of laboratory measurements to guide us. The models we use are educated guesses, stitched together from experiments on Earth and theoretical simulations that cannot capture the full complexity of a real interstellar grain. This uncertainty becomes glaring when we try to explain why molecular hydrogen is abundant in some places and almost absent in others. In dense molecular clouds, the molecule is everywhere, accounting for most of the gas by mass. But in the diffuse gas between clouds, where the density is lower and the radiation field is stronger, the abundance of molecular hydrogen drops sharply. That drop seems to follow a threshold, a critical column density of gas above which the molecules can form faster than they are destroyed by ultraviolet starlight. But the exact position of that threshold depends on the formation rate, and different models give different answers. Observations struggle to settle the debate because molecular hydrogen is famously difficult to detect directly. It has no strong spectral lines in the cold, dense environments where it lives. Most of the time, astronomers see it indirectly by observing the emission from carbon monoxide, a molecule that forms alongside H2 and shares its spatial distribution. But carbon monoxide is not the same as hydrogen. It can be destroyed more easily, or it can freeze onto grains at very low temperatures, breaking the correlation. So we are left with a frustrating gap. The most important molecule for star formation is the hardest to map. In recent years, astronomers have developed new techniques. They look for absorption lines in the ultraviolet light from distant stars, lines that trace the tiny fraction of molecular hydrogen that exists in a higher energy state. These observations have revealed that even in diffuse gas, small clumps of H2 can survive, often in unexpected places. This patchy distribution hints at a formation process that is sensitive to local conditions, not just large averages. It also suggests that dust grains themselves are not uniform. Some regions may have more of the right kind of grains, carbon-rich or having a particular surface structure that promote rapid hydrogen molecule formation. Others may have grains that are less efficient or grains that have been coated with ice, which changes the chemistry entirely. The puzzle deepens when you consider that molecular hydrogen is not just a passive reservoir. It actively shapes its environment. When H2 forms, it releases energy, a small amount of heat that warms the surrounding gas. That warmth can influence whether the cloud collapses or stays stable. It can also drive chemical reactions because H2 is a key ingredient for making many other molecules, including water and complex organic compounds. So the rate at which H2 forms sets the pace for the entire chemical evolution of a molecular cloud. And that pace remains uncertain, a hidden variable in every model of star formation and galaxy evolution. This leads directly into a broader mystery. The interstellar medium hosts a rich and varied chemistry with hundreds of molecules already identified, from simple carbon monoxide to long carbon chains and even amino acids. But how all these pieces fit together, how the formation of the simplest molecule, H2, governs the creation of everything else, is a story still being assembled. Each new observation of a dust grain or a faint spectral line adds another thread to the tapestry, and at the center of it all, the humble hydrogen molecule sits as both the foundation and the enigma, waiting for us to fully understand its quiet, essential role in the cosmos. The same chemistry that builds hydrogen molecules also creates unexpected complexity. You might think the vast, cold emptiness between stars would be a chemical desert, a place where only the simplest atoms survive. But observations reveal something far richer. Astronomers have detected over 200 different molecules in the interstellar medium, ranging from familiar carbon monoxide to long chains of carbon, and even complex organic compounds like formaldehyde, methanol, and the simple sugar known as glycolaldehyde. Ethyl alcohol, the same molecule found in alcoholic beverages, has been spotted floating in the heart of a star-forming cloud. How can such complicated structures assemble in an environment that seems so hostile, with temperatures near absolute zero, densities a trillion times thinner than the air we breathe, and a constant bath of harsh ultraviolet radiation? This is the mystery of interstellar chemistry, the puzzle of how order emerges from chaos on a cosmic scale. In the gas phase, the odds of two atoms meeting and sticking together are vanishingly small. Most molecules would be torn apart by starlight long before they could grow. The secret lies on the surfaces of dust grains. Each tiny grain acts like a miniature chemical laboratory. Atoms and simple molecules drift through space until they land on the cold surface of a grain. There, they can move slowly across the surface, bumping into each other and reacting. This process is called grain surface chemistry. It is how molecular hydrogen forms, and it also builds more complex molecules. Methanol, for example, is thought to form when carbon monoxide lands on a grain and reacts with successive hydrogen atoms. Over time, those reactions can build up entire layers of ice, rich in water, methane, and ammonia. When a nearby star flickers to life, its ultraviolet light or a passing cosmic ray can blast those ices, breaking them apart and allowing the fragments to recombine into larger organic molecules. The result is a molecular inventory far more advanced than simple gas phase models would predict. This has profound implications. The same types of molecules that form in interstellar clouds are the precursors to the building blocks of life. Amino acids, the compounds that make up proteins, have been found in meteorites, and they are believed to originate from the same grain surface chemistry. Sugars, like those that form the backbone of DNA, have been detected in the gas around young stars. These discoveries suggest that the raw ingredients for life are not rare. They are probably common throughout the galaxy, delivered to young planets by comets and asteroids that formed in these molecular clouds, but many questions remain. How do these large molecules survive the violent process of star formation? What role does the local radiation field play in shaping the chemical recipe? And exactly which reactions on grain surfaces produce the most biologically relevant molecules? Laboratory experiments can mimic some conditions, but they cannot fully reproduce the timescales and complexity of space. Every new detection of a molecule, whether it is a long carbon chain or a ring of carbon and hydrogen, adds a clue to the puzzle. The interstellar medium is not a barren void. It is a vast chemical factory, slowly cooking the ingredients for life across billions of years. This chemical complexity is intimately connected to another great mystery, one involving the regions where gas is no longer cold and neutral, but instead becomes hot and ionized, stripped of its electrons by the fierce light of newborn stars. But not all interstellar gas is cold and dark. Spread across the space between stars, there exists a phase of the interstellar medium that glows with a faint, diffuse light, a warm haze of hydrogen that has been partially stripped of its electrons. This is the warm ionized medium, often called the WIM. It is not as hot as the million-degree gas from supernova remnants, but at around 10,000 degrees Kelvin, it is far warmer than the frigid molecular clouds. It is also surprisingly widespread, occupying a large fraction of the volume of the Milky Way and other spiral galaxies. Yet for all its pervasiveness, the warm ionized medium remains a puzzle. The most basic question is simply what keeps it ionized. Ultraviolet light from hot, massive stars is the obvious candidate. Those stars produce immense numbers of Lyman continuum photons, energetic enough to knock electrons off hydrogen atoms. But when astronomers count the known hot stars and estimate their output, the numbers do not add up. There are simply not enough observed Lyman continuum photons to explain the amount of ionization seen in the WIM. Something else must be contributing. The shortfall could come from photons that escape from star-forming regions, traveling far through the galaxy before being absorbed. It could also come from older, cooler stars that are undergoing a short phase as white dwarfs, which can produce a surprising amount of ultraviolet light. Another possibility is that shocks, the shockwaves created by supernova or stellar winds, heat and ionize gas mechanically and not just radiatively. Each candidate has its strengths and weaknesses, but no single source fully resolves the discrepancy. The debate has simmered for decades, with each new observation tightening constraints but never closing the case. The mystery deepens when you look at the vertical structure of the warm ionized medium. In our galaxy, the WIM extends far above and below the disk, forming a thick layer that reaches thousands of light-years away from the plane where most stars lie. This scale height is surprisingly large, nearly twice that of the neutral gas layer. Something must be supporting this warm ionized gas against the pull of gravity, puffing it up into a diffuse halo. That support could come from the same sources that drive turbulence, supernova explosions, and stellar winds, which inject energy and momentum into the surrounding gas. But the details are uncertain. The WIM is not static. It is part of a grand circulation known as the galactic fountain. Hot gas from supernova remnants rises out of the disk, cools as it expands, and eventually falls back down, raining onto the plane in the form of high-velocity clouds. The warm ionized medium sits in the middle of this cycle, a transitional phase between the hot rising gas and the cooler clouds falling back. It connects the disk to the halo, transporting energy and metals across vast distances. Without a clear understanding of the WIM, our picture of how galaxies recycle their gas remains incomplete. And that brings us to the opposite extreme, the phase of the interstellar medium that is so hot it is almost invisible, a ghostly plasma that fills the bubbles and cavities between the stars. The hottest phase of the interstellar medium is almost invisible, a million-degree plasma that glows faintly in X-rays. Astronomers call it the coronal gas or the hot ionized medium, and it is the most extreme temperature extreme in the entire galactic ecosystem. This gas is so hot that atoms are completely stripped of their electrons, leaving only bare nuclei and free electrons zipping around at enormous speeds. It fills the vast cavities and bubbles carved out by supernova explosions and the fierce winds from massive stars. When a supernova detonates, it launches a shock wave that heats the surrounding gas to tens of millions of degrees. Over tens of thousands of years, that gas expands and cools, but it remains incredibly hot by interstellar standards, lingering at around 1,000,000 degrees for millions of years. The mystery is how much of the galaxy this hot phase actually occupies. Estimates for its volume filling factor, the fraction of interstellar space it fills, range from 20 to 60%. That huge uncertainty reflects how hard it is to map something that emits so little light. The coronal gas is so tenuous that only the most sensitive X-ray telescopes can detect its faint glow, and even then the signal is mixed with emission from other hot sources. The cooling mechanisms are another puzzle. At such high temperatures, the gas should radiate away its energy quickly, especially through emission from highly ionized heavy elements like oxygen and iron. But the observed X-ray brightness suggests the gas cools more slowly than simple models predict. Something must be reheating it or slowing the cooling process. Perhaps the hot gas is constantly being refreshed by new supernova explosions, or perhaps magnetic fields suppress the turbulence that would otherwise mix it with cooler material. The coexistence of this million-degree plasma with cold molecular clouds, which are only 10 degrees above absolute zero, seems impossible. In everyday experience, hot and cold air mix quickly, but in space the densities are so low that collisions between particles are rare. The hot gas is incredibly thin, with only a few thousand particles per cubic meter, compared to billions of particles in a cubic meter of cold cloud. Because of this low density, the hot gas exerts very little pressure. It can sit right next to a cold cloud without instantly destroying it, as long as the two are in rough pressure balance. The cold cloud is dense but cold, the hot gas is tenuous but hot, and their pressures can match. This delicate balance allows the interstellar medium to host multiple phases simultaneously, a phenomenon first described by the astrophysicist McKee and Ostraker in their classic model. That model envisions a dynamic, frothy structure where hot bubbles expand into the surrounding gas, compressing and sweeping up material into dense shells. Those shells then cool and fragment, forming new clouds. This cycle is part of the galactic fountain. The hot gas rises above the galactic plane, buoyant because it is less dense than the surrounding medium. As it rises, it expands and cools, eventually becoming dense enough to fall back toward the disk. When it crashes into the galactic plane, it can trigger new star formation and bring fresh metals to regions far from where they were originally forged. Evidence for this fountain comes from observations of high-velocity clouds, clumps of gas falling toward the galaxy at speeds of hundreds of kilometers per second. Their motions and compositions suggest they are recycled material from the hot halo, cooled and returning, but the details remain uncertain. How much material is actually cycled and over what timescales are open questions. The hot interstellar medium is not a static background. It is the engine that drives the galaxy's evolution, connecting the violent deaths of stars to the birth of new ones. And the most dramatic expression of that engine is the interstellar bubble, a cavity carved out by a single star cluster or supernova. These bubbles are where the hot gas is born, where it expands, and where it eventually meets its fate as it cools and mixes back into the colder phases. Understanding bubbles, their sizes, shapes, and lifetimes is the next piece of this puzzle. They are the cradles of the coronal gas, and they may hold the key to unlocking the entire cycle of galactic recycling. Bubbles are not just things that children blow with soap and air. In the interstellar medium, bubbles are cavities carved by violence, and they surround almost every massive star in the galaxy. The easiest one to talk about is the one we live inside, the local bubble. This is a vast, irregular cavity about 1,000 light-years across in which the gas is extremely thin and hot. Our solar system has been drifting through this bubble for millions of years. It was carved by a series of supernova explosions, perhaps as many as 20 of them, that went off in the nearby Scorpius-Centaurus association over the past 10 to 15 million years. The shockwaves from those blasts swept up the surrounding gas into a dense shell, leaving behind a hot, tenuous interior, and while we understand the general idea, many details remain uncertain. Exactly which stars exploded and in what order, how many supernovae were needed to create the bubble we see today, and why does the local bubble have such an irregular, almost lumpy shape? These questions lead into a broader mystery about how all bubbles and shells form across the galaxy. Every massive star, those hotter and larger than our Sun, drives a powerful stellar wind. That wind pushes against the surrounding interstellar medium, creating a small bubble around the star. When the star eventually explodes as a supernova, the blast wave expands into that already cleared region, inflating a much larger bubble. Over time, as more stars in a cluster go supernova, the bubbles can merge, creating enormous superbubbles that span thousands of light years. The structure of these bubbles is often fractal, meaning their edges are not smooth but rough and complicated, with filaments and tendrils branching out in every direction. This fractal nature is a clue to the turbulent processes that shape them, but exactly how turbulence sculpts these boundaries is not well understood. One of the deepest puzzles is why some bubbles keep expanding while others seem to stall. A bubble expands because the hot interior has higher pressure than the surrounding cold gas. But as it grows, the interior cools and the pressure drops. Eventually, if the bubble stops receiving fresh energy from new supernova, it reaches pressure equilibrium and stops expanding. Yet many observed bubbles appear to be still growing even when they are very old. Something must be reheating them or injecting new momentum. That something could be the same cosmic rays and magnetic fields we discussed earlier, which can provide additional pressure. Or it could be that older stars in the cluster continue to blow slower but persistent winds, keeping the bubble inflated. The uncertainties in these models are large. Observing the hot interior of a bubble is extremely difficult because the X-ray emission is faint and easily confused with other sources. So we often see only the cold shell of swept-up gas glowing in radio waves or infrared. From that shell, we try to infer the bubble's history, but many assumptions go into those calculations. The edges of these bubbles are not just passive walls. They are places where star formation is often triggered. When a bubble expands, it plows into the surrounding gas, compressing it into a dense, thin shell. That compression can be enough to make the gas collapse under its own gravity, forming new stars. This is called triggered star formation, and it is one way that the death of one generation of stars directly leads to the birth of the next. You can see examples of this in the famous Eagle Nebula and the Rosette Nebula, where young stars are strung out along the rims of giant bubbles. The mystery is how efficient this triggering is. Is it the dominant mode of star formation in the galaxy, or just a secondary process? The answer affects how we model the entire star formation rate of the Milky Way. Some simulations suggest that as much as half of all new stars could be born in the shells of expanding bubbles. Others argue for a much smaller fraction. Observational tests are tricky because we cannot see the full three-dimensional structure of these bubbles easily. They overlap and blend together, especially in the crowded plane of the galaxy, creating a network of interconnected cavities. This network gives the interstellar medium its porous, foamy appearance, like a sponge or a block of Swiss cheese. The puzzles of individual bubbles are important, but the collective structure they create is just as mysterious. How do these bubbles connect and interact? What determines the typical size and spacing of the cavities? And how does this porous structure affect the propagation of cosmic rays and magnetic fields? These are open questions that link directly to the next structural mystery, the interstellar filaments, because bubbles and shells are not the only large-scale patterns in the gas. There are also long, thin strands of dense material that snake through the galaxy, often at the boundaries of these very bubbles. Understanding how filaments form from the edges of expanding shells is a key part of the story, and it shows how the same forces that create voids also build the threads that may cradle the next generation of stars. Across every molecular cloud, long thread-like structures weave through the darkness. Astronomers call these interstellar filaments, and they are some of the most striking features seen in images of star-forming regions. You have probably seen them before, even if you did not realize it. The famous pillars of creation in the Eagle Nebula are essentially thick, sculpted filaments. And closer to home, the Orion molecular cloud is crisscrossed with them, like veins running through a leaf. These filaments are not random, they are the birthplaces of stars. Almost every young star we observe, including our own sun, is thought to have originated inside one of these cosmic threads, but why they form and why they all seem to share a surprisingly uniform thickness remains one of the great puzzles of the interstellar medium. The mystery begins with the shape itself. A filament is a long, narrow concentration of gas and dust, typically about 1 light-year across but stretching for dozens or even hundreds of light-years in length. In many maps, they appear perfectly aligned with the local magnetic field, as if the field lines are somehow drawing the gas into these stretched-out bundles. That alignment is a strong clue. It suggests that magnetic fields play a crucial role in shaping the gas, perhaps funneling material along the field lines and preventing it from spreading sideways. But the exact mechanism is hotly debated. Some researchers argue that turbulence, the same chaotic churning we discussed earlier, naturally creates filamentary structures as it compresses gas into sheets and then into thin strands. Others point to gravitational instability, the natural tendency of a large cloud to fragment into smaller pieces, which can produce long, skinny structures under the right conditions. Still others believe that magnetic focusing, where the field channels flowing gas into dense lanes, is the dominant driver. Each model can reproduce some observations, but none perfectly explains all of them. One of the most intriguing clues is the characteristic width. When astronomers measure the thickness of dozens of filaments across different clouds, they keep finding the same value, roughly 1/10 of a parsec, which is about 30 trillion kilometers. That number appears again and again, whether the filament sits in a dense, star-rich region or in a more desolate stretch of gas. It is as if there is a universal ruler at work, a fixed scale imposed by the physics of the gas itself. The leading explanation involves the interplay between magnetic fields and turbulence. The idea is that a filament cannot be thinner than the distance that magnetic waves can travel within the time it takes for the gas to cool and collapse. That distance, called the magnetosonic scale, naturally works out to be about 1/10 of a parsec in the typical conditions of a molecular cloud. It is a compelling explanation, but it raises its own questions. The magnetosonic scale depends on parameters like temperature and magnetic field strength, which vary across different clouds. So why does the characteristic width remain so constant? Perhaps those parameters do not vary as much as we think, or perhaps another, unknown mechanism is setting the scale. The role of magnetic fields in stabilizing filaments adds another layer. A filament would normally collapse under its own gravity, fragmenting into cores that form stars. That is exactly what we want for star formation, but if it happens too quickly, every filament would turn into a dense cluster of stars instantly. That does not match the observed slow pace of star formation. Something must be holding the filaments up, preventing them from collapsing all at once. Magnetic fields provide that support. They run along the length of the filament like taut ropes, and they resist being squeezed. The tension in those magnetic ropes slows the fragmentation, allowing stars to form gradually over many millions of years. Yet the strength of the magnetic field required to do this is critical. Too weak, and the filament collapses; too fast, too strong, and it never collapses at all. Observations of magnetic field strength inside filaments are difficult to make, but the few measurements we have suggest the fields are just strong enough to provide the right balance. This fine-tuning feels like another clue, hinting that the relationship between magnetic fields, turbulence, and gravity is precisely calibrated to produce the star formation rates we see. But we do not know why that calibration exists or how universal it is across the galaxy. The mystery of filaments is not just about understanding one structure. It is about understanding the entire process by which a diffuse cloud of gas transforms into individual stars. Filaments are the intermediate stage, the bridge between the large-scale chaos of the interstellar medium and the tiny, dense cores that become new suns. If we can figure out how filaments form and why they have a fixed width, we will unlock a fundamental piece of the star formation puzzle. And that could help us answer even bigger questions about how galaxies build their stellar populations across cosmic time. But before we can fully solve the filament mystery, we need to look closer at the very variations within the gas itself, at the fluctuations in density that give birth to these threads in the first place. The interstellar medium is not a uniform fog but a patchwork of extremes. In some places the gas is so thin that a cubic kilometer of space contains only a handful of particles, while in others the density is 1,000,000 times higher, thick enough to block starlight entirely. And between these extremes there is a whole hierarchy of clumps, sheets, filaments, and vast empty voids. This density structure is not random. It follows a pattern that looks almost the same whether you zoom in or zoom out, like a coastline seen from a plane or the branching of a river delta. That pattern is called fractal, and it is one of the most puzzling properties of the interstellar medium. Measuring this density distribution is surprisingly difficult. Telescopes see only the light that travels through or from the gas, and that light is always integrated along the entire line of sight. A dense little knot hidden behind a thin diffuse haze can look exactly the same as a larger, less dense cloud. Astronomers have to use clever techniques to untangle the three-dimensional structure. They compare emission in different wavelengths, measure how light is absorbed by dust, or use the motions of the gas to infer distances. But every method has its own uncertainties, and the result is a picture that is fuzzy at best. We know the density varies hugely, but we cannot map it with anything close to the precision we would like. That uncertainty has deep implications for star formation. Stars are born only in the densest parts of molecular clouds, the cores that reach a critical threshold where gravity overwhelms the internal pressure. But the exact location of that threshold and how many cores actually form depends on the small-scale structure of the gas. If the gas is clumped into many tiny, dense knots, then star formation proceeds quickly and produces many low-mass stars. If the clumps are larger and more diffuse, the process is slower and favors larger stars. The fractal nature of the gas determines the outcome, and we do not yet have a clear handle on why the fractal pattern exists in the first place. The leading explanation is turbulence. You already know that turbulence stirs the gas across a vast range of scales, from light years down to the size of planetary orbits. This turbulent motion naturally creates a cascade of density fluctuations. Imagine a pot of soup boiling vigorously. The bubbles and eddies at the surface are all different sizes, and they constantly merge and split. The interstellar medium behaves similarly, except the soup is made of gas and magnetic fields, and the boiling is driven by supernova and stellar winds. The resulting density field is not smooth but full of lumps and voids, and those lumps themselves contain smaller lumps and so on down to the smallest scales. This self-similar structure is the fractal nature we observe, but turbulence alone cannot fully explain it. The magnetic field and gravity also play a role, and the interplay of all three forces is still not fully understood. Some simulations produce fractal clouds that match observations, but only when the input parameters are finely tuned. others produce clouds that are too smooth or too fragmented. The mystery is deepened by the fact that the fractal dimension, a number that describes how the clumpiness changes with scale, seems to be nearly the same in many different clouds across the galaxy, from nearby star-forming regions to the far side of the Milky Way. That consistency hints at a universal physical process, but we have not yet identified it. This puzzle connects directly to another one. If the density of the interstellar medium varies so much, then so does its chemical composition, because different environments process elements in different ways. Some regions are enriched with heavy elements from recent supernova, while others are relatively pristine. The variations in metallicity, the abundance of elements heavier than hydrogen and helium, are a fingerprint of the galaxy's history. They tell us where gas has been recycled, where it has been ejected, and where it has fallen back in. And like the density fluctuations, these metallicity variations follow a pattern that is not yet fully mapped. So the clumpiness of the gas is not just a structural curiosity. It is the key to understanding how the galaxy breathes, how it mixes the ashes of old stars into the birthplaces of new ones. And that leads directly into the question of why some parts of the interstellar medium are so much richer in metals than others, a mystery that has puzzled astronomers for decades. The galaxy has a hidden chemical fingerprint that changes with distance from its center. Astronomers call this the metallicity gradient, and it is one of the most revealing patterns in the interstellar medium. Far from being uniform, the abundance of elements heavier than hydrogen and helium, what scientists call metals, gradually decreases as you move outward from the galactic center. In the inner regions, where star formation has been vigorous for billions of years, successive generations of stars have enriched the gas with oxygen, carbon, iron, and other elements. Each supernova scatters these metals into the surrounding medium, building up a higher concentration near the crowded core. Farther out, in the quieter spiral arms and the dim outskirts, fewer stars have lived and died, so the gas remains more pristine. This gradient is a fossil record of the galaxy's entire history of star birth, gas inflow and gas outflow. But when astronomers measure these gradients across different galaxies, they find a confusing variety. Some galaxies have steep gradients where the metal abundance drops sharply over a short distance. Others have shallow gradients, almost flat, where the composition barely changes from the core to the edge. And in a few cases, the gradient even flattens or reverses in the outer regions. What causes these differences? One leading idea involves the galactic fountain we discussed earlier. When supernova explode in the inner disk, they heat gas and lift it into the halo. That gas then cools and rains back down, but it can fall far from its original location. This mixing process can smooth out gradients, spreading enriched gas outward and diluting it with fresh infalling material. If the fountain is vigorous, the gradient becomes shallow. If it is weak, the gradient remains steep. Yet the details of this mixing depend on many factors: the galaxy's mass, its rotation speed, the frequency of supernova, and the amount of gas falling in from intergalactic space. Computer models can produce a range of outcomes, but observations keep challenging them. Another mystery is why some galaxies show a flattening of the gradient in their outermost regions. This flattening might indicate that gas accretion from the cosmic web is particularly important there, bringing in metal-poor material that dilutes the local enrichment. Or it could be that those outer regions have had a burst of star formation relatively recently, raising their metallicity quickly. Without a clear model, the flattening remains a puzzle. There is also the question of how gradients evolve over time. The Milky Way's gradient today is not what it was a billion years ago. As the galaxy ages and the rate of star formation slows, the gradient may become steeper or shallower depending on how gas continues to flow. Some simulations suggest that the gradient was steeper in the past when the galaxy was more active and has since relaxed, but we cannot travel back in time to check. Instead, we look at distant galaxies at different stages of their lives, measuring their gradients with powerful telescopes. Those observations are still sparse and uncertain. This entire story of chemical enrichment becomes even more intriguing when we step outside the grand spiral galaxies and look at the smallest stellar systems. Dwarf galaxies are the most common type of galaxy in the universe, and their interstellar medium behaves very differently from the Milky Way's. Their gravity is weaker, their star formation is more sporadic, and they can lose enriched gas more easily. Their metallicity gradients, or the lack thereof, might hold the key to understanding how these tiny systems survive and evolve. The shift in scale is dramatic, but the same physical processes are at work, just under more extreme conditions. Dwarf galaxies push the interstellar medium to its limits. These tiny stellar systems, containing only a fraction of the stars found in a galaxy like the Milky Way, host some of the most extreme and mysterious conditions in the cosmos. Their interstellar medium is a puzzle that challenges everything we think we know about how gas behaves, how stars form, and how galaxies evolve. The first mystery is the composition of that gas. Dwarf galaxies have very low metallicity, meaning the abundance of elements heavier than hydrogen and helium is a tiny fraction of what we see in our own galactic neighborhood. Some dwarf galaxies are so metal-poor that their gas is nearly pristine, similar to the material left over from the Big Bang itself. This makes them invaluable laboratories for studying the early universe, but it also creates a host of problems. With so few heavy elements, the gas is missing the key ingredients that normally help clouds cool and collapse. In a metal-rich environment, carbon and oxygen atoms radiate heat efficiently, allowing a cloud to lose energy and contract under gravity. In a metal-poor dwarf, those cooling channels are almost absent. The gas should stay hot and diffuse, unable to form stars. Yet dwarf galaxies do form stars, sometimes in dramatic bursts that can double their stellar mass in just a few million years. How does the gas cool enough to collapse? One possibility is that molecular hydrogen, which can form even in low metallicity gas, takes over the cooling role. But molecular hydrogen is a weak coolant compared to carbon monoxide or oxygen. The process would be slow and inefficient, yet the observed bursts suggest that something else is helping. Another idea is that turbulent mixing with small amounts of enriched gas from earlier generations of stars provides the necessary cooling agents, but that requires a delicate balance and raises the question of how those first stars enriched the gas in the first place. The dust content in dwarf galaxies is also puzzling. Dust grains are essential for shielding molecules from ultraviolet radiation and for providing surfaces where chemical reactions occur. But in dwarf galaxies, the dust-to-gas ratio is typically very low, often less than 1% of what we find in the Milky Way. That means ultraviolet light from young stars can penetrate deep into the gas, destroying molecules before they have a chance to build up. This should suppress the formation of complex molecules, yet some dwarf galaxies show signs of molecular gas and even active star formation. The chemistry itself must be different, favoring molecules that can survive in harsher conditions or relying on unusual pathways to build them. Observations of carbon monoxide, the standard tracer of molecular gas in normal galaxies, often fail to detect it in dwarfs even when star formation is ongoing. This suggests that either the molecular gas is present but carbon-poor, or that the gas is in a form we do not yet know how to detect. The mystery deepens when we consider that dwarf galaxies can lose their gas very easily. Their shallow gravitational potential means that a single supernova explosion can blow a substantial fraction of the interstellar medium right out of the galaxy, sending it streaming into intergalactic space. This process, known as feedback, should strip the galaxy of its star-forming fuel, leaving it barren. Yet many dwarf galaxies have gas reservoirs that last for billions of years despite continuous star formation. What slows the loss? Perhaps magnetic fields or the geometry of the gas play a protective role, but we lack the detailed observations to confirm this. Another possibility is that dwarf galaxies constantly accrete new gas from the surrounding cosmic web, replenishing what they lose. That accretion, however, is hard to detect directly because the inflowing gas is thin and hot. The balance between loss and gain remains one of the most active areas of research. The leaking of ionizing photons adds another layer. In normal galaxies, most of the ultraviolet light from young stars is absorbed by the surrounding gas and dust. But in dwarf galaxies, the low dust content and the porosity of the interstellar medium allow a significant fraction of these energetic photons to escape into intergalactic space. This escaping radiation is thought to be a key driver of reionization, the period in the early universe when neutral hydrogen was split into protons and electrons. Understanding how dwarf galaxies retain or lose their gas and how their interstellar medium behaves is therefore not just a curiosity. It is a window into the very first galaxies that formed after the Big Bang. Those early galaxies were also metal-poor, dust-poor, and small, and they faced the same challenges. Their interstellar medium must have operated under similar extreme conditions, and the puzzles we see in nearby dwarf galaxies are echoes of that ancient era. By solving the mystery of how dwarf galaxies manage to form stars despite their inhospitable environment, we get closer to understanding how the very first stars and galaxies lit up the dark universe. And that journey leads us back in time to a period when the interstellar medium was not just a background fog, but the primary stage on which the cosmic drama began. Looking further back in time to galaxies that existed when the universe was only a few billion years old reveals an interstellar medium unlike anything we see today. Peering across such vast distances is incredibly difficult. The light from these early galaxies has been stretched by the expansion of space, shifting even visible wavelengths into the infrared. Their interstellar gas is faint, and their dust obscures what little light their stars produce, so astronomers rely on clever techniques, especially absorption lines. When a bright background source, like an even more distant quasar, shines through the gas of a foreground galaxy, its light imprints the signature of that gas. Every element leaves a fingerprint, and by reading those fingerprints, researchers can measure the gas density, composition, temperature, and motion. More recently, the Atacama Large Millimeter/Submillimeter Array, or ALMA, has opened a new window. ALMA detects the faint glow of cold gas and dust, revealing structures that were hidden before. What these instruments have found is stunning. Early galaxies appear to have gas fractions far higher than the Milky Way, sometimes 10 times more gas relative to their stars. The gas is also churning with intense turbulence, moving at speeds that would tear apart the molecular clouds we see nearby. The dust itself seems different, perhaps less abundant or made of different materials, shaped by an environment rich in fresh metals from the first generations of stars. The biggest mystery is how these galaxies assembled their enormous gas reservoirs so quickly. The universe was young, only a few billion years old. Gravity should have been pulling gas together, but not that fast. Something must have driven rapid inflows of pristine material from the cosmic web, or perhaps mergers between smaller galaxies delivered the gas in sudden bursts. Observations show that many high redshift galaxies are clumpy, with massive star-forming regions scattered across their disks, not smoothly distributed like modern spirals. That clumpiness might be a clue, indicating that the gas was so dense and turbulent that it fragmented on large scales. Modeling the chemistry of these early systems is a major challenge. The same molecules we use as tracers in our own galaxy, like carbon monoxide, behave differently in metal-poor, highly turbulent gas. The ratio of carbon monoxide to molecular hydrogen, which we rely on to weigh clouds, likely changes with metallicity and radiation field. So estimates of star-forming gas in early galaxies are uncertain by factors of 2 or 3. Some researchers suggest that a large fraction of the molecular gas might be dark, meaning we cannot see it with current telescopes because it lacks the heavy elements needed to emit detectable signals. Understanding that hidden reservoir is critical because it directly feeds the furious star formation seen in these ancient systems. Some of these galaxies form stars at rates thousands of times higher than the Milky Way, turning their entire gas supply into new suns in just a few 100 million years. That process, called a starburst, must be fueled by a continuously replenished interstellar medium, but the details of how that fuel is delivered and processed remain a puzzle. The link between the interstellar medium and star formation is perhaps most extreme in these early galaxies, and solving the mysteries of their gas will tell us how the universe built its first great cities of stars. That furious star formation in early galaxies comes at a cost. The very same massive stars that light up those brilliant bursts of new birth also unleash forces that tear their surroundings apart. With their intense ultraviolet radiation, powerful stellar winds, and the violent release of energy when they reach the end of their lives, these stars inject staggering amounts of energy back into the interstellar medium. This process is collectively known as feedback, and it is one of the most important yet least understood mechanisms in all of astrophysics. Without feedback, a galaxy would simply convert all its gas into stars within a few 100 million years, leaving no fuel for future generations. Observations tell us that does not happen. Most galaxies form stars slowly over billions of years, and many are actively quenched, meaning their star formation shuts down entirely. Something must be regulating the process, and that something is feedback. The mystery lies in how this feedback actually works and how efficiently it couples to the surrounding gas. When a massive star blows a wind or a supernova sends out a shock wave, that energy does not just vanish. It pushes against the interstellar medium, heating it, compressing it, and sometimes blowing it clear out of the galaxy. Those outflows, known as galactic winds, have been observed in many star-forming galaxies, carrying gas enriched with heavy elements into the surrounding halo and even beyond. But the energy budget is tricky to calculate. A single supernova releases as much energy as the Sun will produce in its entire lifetime of 10 billion years. Yet most of that energy is carried away by neutrinos, which barely interact with matter, and the rest quickly radiates away as the hot gas cools. Only a small fraction goes into driving the bulk motion of the gas. That fraction, called the coupling efficiency, is extremely uncertain, with estimates ranging from a few percent to nearly half. If the coupling is low, feedback is weak, and galaxies would form too many stars. If it is high, feedback would blow all the gas away instantly, strangling star formation. The truth lies somewhere in between, but we have not pinned it down. Computer simulations struggle to capture this physics because the relevant scales are so different. The energy injection happens in a region no larger than a few light years, yet its effects propagate across tens of thousands of light years, shaping the entire galaxy. To simulate both scales simultaneously requires enormous computational power and often leads to approximations that can miss key details. Some models treat feedback as a sub-grid recipe, a simplified rule that mimics the effect without resolving the actual explosions. Others try to include individual supernova remnants, but they remain limited to small volumes or short timescales. The result is that different simulations produce wildly different star formation histories and galaxy morphologies, all depending on how they handle feedback. Observations are the ultimate arbiter, but they are also challenging. We can see the hot gas in galactic outflows, we can measure the motion of cool clouds being swept up, and we can detect the bubbles and shells carved by feedback. But we cannot easily measure the exact energy input or the fraction that actually drives the outflow. So the link remains a statistical puzzle, one that requires combining many lines of evidence. The impact of feedback goes beyond just slowing star formation. It also stirs and enriches the interstellar medium, mixing fresh heavy elements into the gas and creating the density fluctuations that trigger new star formation elsewhere. In this way, feedback acts as both a destroyer and a creator, a cycle of birth and disruption that we are only beginning to map. And at the center of many galaxies, including our own Milky Way, there lies an even more powerful engine of feedback, a supermassive black hole that can inject energy far exceeding that of all the stars combined. That black hole at the galactic center can unleash forces that reshape an entire galaxy. When a supermassive black hole actively consumes gas, it does not just swallow the material quietly. The infalling matter heats up to extreme temperatures, releasing vast amounts of energy in the form of radiation, along with powerful jets of particles that blast outward at speeds close to light. These twin jets can extend for hundreds of thousands of light years, punching through the interstellar medium of the host galaxy and sometimes even into the space between galaxies. This process is called active galactic nucleus feedback, and it is one of the most violent and mysterious interactions in the cosmos. The puzzle lies in how this energy couples to the gas that surrounds the black hole. On paper, the energy output from an active nucleus is staggering, often exceeding the combined light of all the stars in the galaxy. In theory, that should be more than enough to heat or even blow away all the cold gas in the galaxy, shutting down star formation for billions of years. Yet observations show a confusing picture. In some galaxies, astronomers see clear signs of disruption. Fast-moving outflows of gas race outward at thousands of kilometers per second, far faster than any supernova-driven wind. The gas is heated to millions of degrees, and the molecular gas reservoirs that would normally form stars are swept away or destroyed. These galaxies often have little or no ongoing star formation, suggesting the black hole has indeed quenched its host. But in other galaxies that host active nuclei, the interstellar medium appears remarkably undisturbed. The same cold gas clouds persist, star formation continues at a normal rate, and the galaxy shows no obvious signs of being blasted apart. Why the difference? The leading idea is that not all of the black hole's energy actually reaches the interstellar gas. Much of it might escape along the jets, which are pointed away from the galactic disk. The jets are narrow and highly collimated, so they only directly affect a small fraction of the gas. The radiation, meanwhile, can be absorbed by dense material very close to the black hole, heating it but not driving large-scale outflows. The coupling efficiency, the fraction of the black hole's energy that actually pushes or heats the galaxy's gas, might vary enormously depending on the geometry of the accretion flow, the density of the surrounding material, and the orientation of the jets. This uncertainty makes it extremely difficult to predict whether a given active nucleus will quench its galaxy or leave it untouched. Observations have advanced our understanding, especially from space-based X-ray telescopes that detect the hot gas and from millimeter telescopes that map the cold molecular outflows. In some of the most studied systems, astronomers have measured the mass and speed of the outflows, calculating the rate at which gas is being ejected. The numbers are impressive, sometimes thousands of solar masses per year, enough to deprive the galaxy of its star-forming fuel in just a few million years. But those measurements come with large error bars. We are still not sure whether these outflows actually escape the galaxy entirely, or whether they simply rise into the halo and eventually fall back like a giant galactic fountain. If they fall back, the quenching might be only temporary and the galaxy could resume forming stars later. The long-term impact of AGN feedback remains one of the most open questions in galaxy evolution. Some cosmological simulations rely on it to explain why massive galaxies stop forming stars, while others find that they need it to prevent galaxies from growing too large. Without a precise understanding of how the black hole and the interstellar medium exchange energy, our models remain incomplete. This puzzle connects directly to the broader cycles of gas that drive galaxy evolution. The interstellar medium is constantly being enriched, heated, cooled, and reshaped by the stars within it, and now we see that the central black hole can act as an additional, powerful driver. How these processes balance over cosmic time, whether the black hole ultimately helps or hinders the formation of stars, and why some galaxies respond so differently than others, are questions that tie together the smallest scales of a black hole's event horizon with the largest scales of a galactic halo. And that link between the microscopic and the macroscopic is what makes the interstellar medium such a rich and enduring mystery. It is the stage where the entire story of galaxy evolution plays out, from the birth of the first stars to the eventual quiet death of even the most brilliant galaxies. A galaxy is not a closed system. It breathes. Stars are born from gas, they live and they die, but the gas they consume does not simply reappear. Over billions of years, the star formation rate of a galaxy like the Milky Way should have exhausted its interstellar fuel long ago. Yet we see new stars still forming, young clusters glowing in the spiral arms, and vast molecular clouds ready to collapse. Something must be replenishing the supply. That something is the ongoing accretion of gas from outside the galaxy. But where exactly that gas comes from, how it arrives, and how efficiently it is converted into stars remains one of the most stubborn mysteries of the interstellar medium. The challenge begins with the sources. The most obvious candidate is the cosmic web, the vast network of filaments that connects galaxies across the universe. This tenuous medium contains enormous reservoirs of hydrogen and helium, left over from the Big Bang, that have never been processed by stars. Gravity pulls this pristine gas toward galaxies, funneling it along the filaments and into the dark matter halos that surround them. Once inside the halo, the gas is heated by shocks to millions of degrees. Then it must cool and condense before it can join the interstellar medium. But the process is far from straightforward. Observations show that many galaxies, including our own, are surrounded by a circumgalactic medium, a diffuse halo of gas that absorbs light from distant quasars. This circumgalactic gas is rich in heavy elements, meaning it has been enriched by previous generations of stars. It cannot be purely primordial. Instead, it is a mixture of fresh infalling material and gas that has been blown out of the galaxy by supernova and later fallen back. That recycled gas, sometimes called a galactic fountain, is a second major source. The same energetic feedback we discussed earlier that drives outflows also creates a cycle. Hot gas rises, cools, and rains down again, carrying metals and energy with it. But quantifying the relative contribution of fresh infall versus recycled gas is extremely difficult. We can see the outflows, but tracing the return flow is like trying to measure the rain in a storm when you are standing inside the cloud. A third source is galaxy mergers. When two galaxies collide, their interstellar media merge, delivering a sudden burst of fresh fuel. In the early universe, such mergers were common and drove the furious starbursts we see in distant galaxies. But in the present-day Milky Way, major mergers are rare. Instead, the galaxy may be slowly accreting gas from small, dwarf companions or from streams of gas stripped from them by tidal forces. One such stream, the Magellanic Stream, is a long ribbon of gas trailing behind the large and small Magellanic Clouds as they orbit our galaxy. This stream is slowly being incorporated into the Milky Way, adding about a solar mass of gas every year. That is a tiny amount compared to the total gas reservoir, but over billions of years it adds up. Even so, measuring the exact accretion rate across the entire galaxy is fraught with uncertainty. Different methods give numbers that vary by a factor of 10. Some estimates suggest the Milky Way is gaining gas at a rate sufficient to sustain its current star formation, while others imply a slow decline with the galaxy gradually running out of fuel. This uncertainty is not just academic. It determines whether our galaxy will continue forming stars for billions of years or fade into a quiet, red collection of old stars. The mystery deepens when you consider how inefficient the process actually is. Most of the gas that falls onto a galaxy does not end up forming stars. Instead, it remains in the circumgalactic medium, or it is ejected back out by the very feedback processes it helped to power. In many galaxies, the star formation efficiency, the fraction of gas converted into stars per unit time, is only a few percent. That means 97% of the available gas is simply sitting there waiting. Why is it so inefficient? Turbulence and magnetic fields are the likely culprits. As we have seen, the interstellar medium is not a calm pool but a churning, magnetized storm. Turbulence provides support against gravitational collapse, keeping much of the gas at a low density where stars cannot form. Magnetic fields add additional tension, resisting compression and funneling gas along field lines rather than letting it collect into dense cores. The same forces that shape the density fluctuations in molecular clouds also slow the overall conversion of gas into stars. So the accretion of fresh gas is only half the story. The other half is how that gas is processed once it arrives, and the answer seems to be that the interstellar medium itself is a bottleneck. It regulates the flow of gas from the cosmic scale down to the scale of individual stars, and it does so with a remarkable inefficiency that keeps galaxies alive for billions of years. This regulation points directly to the role of magnetic fields in the cycle. Magnetic fields are not just passive threads woven through the gas, they can control how gas accretes onto the galaxy in the first place. When pristine gas from the cosmic web approaches a galaxy, it must cross the magnetic field lines that surround the galactic disk. These fields can deflect or slow the inflow, channeling it into specific paths or even preventing it from reaching the disk at all. The efficiency of this magnetic barrier depends on the field's strength and orientation, both of which are poorly known. Some simulations suggest that strong magnetic fields can reduce the accretion rate by a factor of 2 or more, effectively starving the galaxy of fuel. Others find that the fields are too weak to make a difference. The truth likely lies somewhere in between, and it varies from galaxy to galaxy, so the magnetic field is not just a detail. It is a key player in the grand cycle of gas, deciding how much fuel gets delivered, how it is mixed, and how efficiently it is turned into stars. Without understanding it, we cannot close the budget on the interstellar medium's life cycle. And that cycle, the birth, death, and rebirth of gas across cosmic scales, is the very engine that drives the evolution of galaxies. The puzzle of how that gas arrives and why it so stubbornly resists forming stars is far from solved, but every new observation of a quasar absorption line or a radio map of the circumgalactic medium brings us a step closer to understanding the hidden plumbing of the universe. The magnetic fields threading the spiral arms of our galaxy are far stronger than they have any right to be. Observations reveal fields of several microgauss in the diffuse gas, and inside the dense molecular clouds the strength can reach hundreds of microgauss. That might sound tiny, but these fields exert tremendous influence, shaping the motion of gas, guiding cosmic rays, and even helping to decide where stars form. Yet the puzzle is this: where did all that magnetic energy come from? The universe began with only the faintest of magnetic seeds, perhaps generated by tiny fluctuations in the early cosmos or by the motion of plasma in the first stars. From those incredibly weak beginnings, the fields we see today had to be amplified by a factor of 1,000,000 or more. The leading explanation is the dynamo theory, a process that borrows from the same physics that generates the magnetic field of the Earth and the Sun. In a dynamo, the swirling motion of electrically conducting fluid, in this case, the ionized gas of the interstellar medium, stretches and twists the magnetic field lines, amplifying them over time. But the interstellar dynamo is far from simple. It requires a specific kind of turbulent motion, one that is both chaotic and organized. The rotation of the galaxy provides a large-scale twist, while supernova explosions and stellar winds generate the turbulent churning on smaller scales. Together, they can, in theory, build up a strong, ordered field, but the details are still debated. Computer simulations struggle to reproduce the observed field strengths without making assumptions that may not hold true in reality. The rate of amplification, the saturation level, and the role of the galactic fountain all remain uncertain, and there is an even deeper puzzle. Once the field is strong, it does not just sit passively. It actively participates in the evolution of the interstellar medium. It can support a molecular cloud against gravitational collapse, providing a kind of magnetic pressure that resists the inward pull of gravity. This is one of the main reasons why star formation is so inefficient, but at the same time, the same magnetic field can channel outflows from young stars and supernova remnants, funneling hot gas and cosmic rays away from the disk and into the halo. So the field is both a stabilizer and a conduit, a paradox that astronomers are still trying to untangle. In some clouds, the magnetic field lines are aligned with the long axis of the cloud, allowing gas to flow along them but preventing collapse perpendicular to them. In others, the fields are perpendicular to the cloud, creating a sort of magnetic wall that slows or diverts inflows. Which configuration dominates and under what conditions is unknown. This dual role ties directly into another great mystery of the interstellar medium. What happens when a shock wave, a supersonic disturbance from a supernova or a stellar wind, slams into a region threaded by a strong magnetic field? That collision creates a complex interaction that can amplify the field even further, heat the gas, and produce a cascade of particles that glow in radio waves and X-rays. The study of interstellar shocks is the next frontier in understanding how the magnetic field and the gas constantly reshape each other, and it is a story that begins with a simple question: how does a shock wave actually change the magnetic fabric of space? A shock wave racing through the interstellar medium is one of the most violent events in the cosmos. But what makes these shocks truly mysterious is that the gas is so incredibly thin that ordinary collisions between particles are almost non-existent. In a typical shock on Earth, like the one created by a supersonic jet, molecules literally slam into each other, transferring energy and creating a sudden jump in pressure and temperature. In space, the density is 1 billion times lower. Particles can travel light years between encounters, so how does the shock transfer its energy? The answer lies in magnetic fields and turbulence. The shock is mediated not by particle collisions but by electromagnetic forces. As the supersonic blast wave from a supernova or a stellar wind plows into the surrounding gas, it creates a thin, invisible boundary where the magnetic field is suddenly compressed and twisted. This compression generates intense electric fields that can accelerate charged particles to near light speed, turning them into cosmic rays. At the same time, the magnetic field itself oscillates and breaks into turbulence, dissipating the bulk of the shock's energy into heat. This is called a collisionless shock, and it is one of the most fascinating and poorly understood phenomena in the interstellar medium. The mystery deepens when you try to measure how much of the shock's energy actually goes into accelerating cosmic rays versus how much becomes thermal heat. Observations of supernova remnants, the expanding shells left behind by exploded stars, show that the fraction can vary enormously from one remnant to another. Some remnants are bright in gamma rays, a signature of cosmic rays interacting with nearby gas, while others are dominated by X-rays from hot thermal plasma. The balance seems to depend on the age of the remnant, the strength of the surrounding magnetic field, and the density of the gas it is plowing into. But the exact physics that determines this split remains unclear. It is a crucial piece of the energy balance puzzle of the entire interstellar medium, because shocks are one of the primary ways that energy from supernova is redistributed across the galaxy. If too much goes into cosmic rays, they can escape and carry energy away, while if too much goes into heat, it can support the hot phase of the interstellar medium and drive outflows. The uncertainty in this partition directly affects our models of galaxy evolution. Now, as a shock wave passes through a cloud of gas and dust, it does not just accelerate particles and heat the gas. It also physically shreds the tiny dust grains that drift through space. The same violent compression and turbulent eddies that accelerate cosmic rays can also cause dust grains to collide with each other at high speeds, shattering them into smaller fragments. In extreme cases, the grains can be completely vaporized, erased by the intense heat of the shock. This destruction process is remarkably efficient. Studies suggest that a single supernova sweeping through a region can destroy a significant fraction of the dust within its reach. Yet we know that dust still exists in old supernova remnants and throughout the interstellar medium, so something must be creating new dust just as fast as it is being destroyed. The leading candidates for dust formation are the same stars that cause the destruction. In the cool, dense outflows of aging stars, particularly in the envelopes of red giants and the ejecta of supernova themselves, atoms condense into solid particles, building the tiny grains that will later be scattered across the galaxy. The balance between dust destruction and dust growth is another open question. How quickly do new grains form, and how efficiently do they survive the next shock that comes along? The answer determines the amount of dust available to shield molecular clouds, to catalyze the formation of hydrogen molecules, and to provide the raw material for planets. Every time a shock tears through space, it reshapes the chemical and physical landscape, destroying some structures while seeding the conditions for new ones. This cycle of destruction and rebirth is woven into the very fabric of the interstellar medium, and the shock waves are the instruments of its constant transformation. Despite the constant rain of destructive shocks, interstellar dust somehow endures. You might expect that after billions of years of supernova blasts and stellar winds sweeping through the galaxy, every tiny grain would have been shattered or vaporized a dozen times over. Yet when astronomers look at the dust in our galactic neighborhood, they find it is abundant enough to redden starlight, to shield molecular clouds, and to provide the surfaces where the first chemical bonds of star formation take hold. Something must be rebuilding the dust just as fast as it is torn apart, and the puzzle is that we do not fully understand how that rebuilding process works or how quickly it happens. The growth of dust grains happens in the cold, dense cores of molecular clouds. There, atoms and simple molecules drifting through the gas can land on the surface of a grain and stick. Over time, these accreted layers build up, forming mantles of ice that coat the original silicate or carbon core. In the densest regions, the mantles can grow to be many times thicker than the grain itself. This process is called accretion, and it is the primary way that dust grains increase in mass and size. But the rate of accretion depends on the density of the gas, the temperature, and the chemical composition of the surrounding material. In a typical dense core, it might take a few million years for a grain to double its mass. That sounds slow, but it is fast enough to replenish the dust that is constantly being destroyed in the wider interstellar medium. On the other side of the balance sheet is destruction. When a shock wave passes through a cloud, the fast-moving gas can collide with dust grains and knock atoms off their surfaces. This process is known as sputtering. In a strong shock, the grains can be completely eroded down to their bare cores, and in the most violent cases, the cores themselves can be shattered into tiny fragments. The efficiency of sputtering depends on the speed of the shock and the density of the gas. Even a modest shock traveling at 50 kilometers per second can strip away a significant fraction of a grain's mantle. Supernova remnants, which can drive shocks at hundreds of kilometers per second, are particularly devastating. Models suggest that a single supernova sweeping through a region can destroy up to half of the dust within its reach. Yet when we add up all the supernova that have occurred in the Milky Way over its lifetime, the numbers imply that all the dust in the galaxy should have been destroyed many times over. So why is the dust still there? The answer seems to lie in the patchiness of the interstellar medium. Dust destruction is not uniform. Most supernova remnants expand into the thin, hot gas of the interstellar bubbles where the dust density is already low. The dense molecular clouds where most of the dust resides are often far from the nearest supernova, or they are shielded by the very gas and dust that surrounds them. When a shock does reach a dense cloud, it is often slowed and weakened, reducing its destructive power. In other words, the dust survives because it hides in the densest, coldest places, the very same places where accretion is most active. This creates a kind of refuge. In these protected environments, grains can grow faster than they are destroyed, maintaining a steady supply of dust that is then slowly mixed back into the wider interstellar medium by turbulence and stellar feedback. The implications of this balance are profound. The amount of dust in a galaxy directly affects how much starlight is absorbed and re-emitted, how efficiently molecules form, and how quickly gas cools. If the dust budget were too low, star formation would slow down and the galaxy would evolve differently. Yet our models of dust growth and destruction still have large uncertainties. The timescale for accretion in dense clouds is poorly constrained because it depends on the exact composition of the gas and the number of free atoms available. The efficiency of sputtering in shocks is also uncertain because we do not know the precise structure of the grains, their porosity, or how they are held together. Different models give results that vary by factors of 5 or more. That uncertainty ripples through every calculation of the interstellar medium's evolution, from the chemistry of molecular clouds to the energy balance of the entire galaxy. This mystery connects directly to the missing baryons puzzle we discussed earlier. Dust makes up only a tiny fraction of the ordinary matter in the universe, less than 1% of the mass of the gas. But it is disproportionately important because it controls so many of the processes that govern the interstellar medium. If our models overestimate dust destruction, we might think that more dust is being created than actually is, leading to errors in our estimates of the total amount of heavy elements locked up in grains. Those heavy elements, carbon, oxygen, silicon, and iron, are a significant part of the missing baryon budget. They are hiding not just in hot gas, but also in the solid particles that drift between the stars. Understanding how dust grows and dies is therefore a key step toward closing the gap between the visible and predicted matter in the universe, and that leads directly into one of the most fascinating chapters of interstellar chemistry. Carbon is the fourth most abundant element in the cosmos, and it is the backbone of organic molecules. Much of the carbon in the interstellar medium is locked up in dust grains, either as graphite-like particles or as complex organic mantles. But a significant fraction exists as free atoms and simple molecules floating in the gas. The exchange between these two reservoirs, the dust and the gas, is the central mystery of interstellar carbon chemistry. How does carbon move from grains back into the gas, and how does it recondense? The answer determines what kind of molecules are available to build planets and eventually life. And that transition from the solid dust to the gaseous carbon is the next great puzzle waiting to be unraveled. Carbon is the architect of complexity in the universe, yet we cannot account for where it all hides. This is the carbon crisis, a puzzle that has frustrated astronomers for decades. When we add up all the carbon we can see in the interstellar medium, in gas clouds, in dust grains, and in the diffuse space between them, we keep coming up short. The models predict that a certain amount of carbon should exist in the gas phase, as atoms or simple molecules that produce observable spectral lines. But our observations consistently find more gas phase carbon than those models allow. Something is missing from our inventory, some hidden reservoir that holds the extra carbon without revealing itself in the usual ways. The leading candidates for that missing carbon are polycyclic aromatic hydrocarbons, or PAR. These are large, flat molecules made of dozens of carbon atoms arranged in rings like tiny sheets of graphene. They float in the interstellar medium, absorbing ultraviolet light and then re-emitting it at longer infrared wavelengths. That glow is a distinctive fingerprint, and we have detected PAHs across the galaxy. But we do not know exactly how many there are, what sizes they come in, or how much total carbon they lock up. Estimates vary wildly, from a few % to half of all the carbon in the interstellar medium. The uncertainty is so large that the carbon crisis remains unresolved. Another candidate is the fullerene family, the cage-like molecules made entirely of carbon, such as the famous buckeball with 60 carbon atoms. These have been detected in some planetary nebulae and interstellar clouds, but their abundance is even harder to pin down. They may be a minor reservoir or a major one, depending on local conditions. The situation is further complicated by the fact that carbon moves between phases. Atoms can stick onto dust grains, building icy mantles, and then be released back into the gas when a shock or a nearby star heats the grain. This cycle is dynamic, and the balance between solid and gaseous carbon shifts over time and across regions, so the puzzle is not just a matter of a single number. It is a map of how carbon is processed, stored, and recycled in the interstellar medium. Understanding this map is critical because carbon is the backbone of organic chemistry. Every molecule that could lead to life, every amino acid, every sugar, every nucleotide, relies on carbon's ability to form stable chains and rings. If we cannot explain where the carbon is and how it moves, we cannot fully understand the chemical pathways that lead to the building blocks of life. This brings us to the next great element in the cosmic recipe: oxygen. Oxygen is the third most abundant element in the universe, and it is just as mysterious as carbon. Most of the oxygen in the interstellar medium is locked up in water ice, frozen onto dust grains in cold, dense clouds. But water is not just a simple molecule. It is the key to understanding how planets get their oceans and how life finds a solvent. The puzzle of interstellar oxygen and water is intimately tied to the carbon story, because the two elements often compete for the same hydrogen atoms, forming either water or carbon monoxide. The ratio of these molecules and the conditions that favor one over the other is a delicate balance that we are only beginning to measure. As we move from carbon to oxygen, we step into a new layer of complexity, one that connects the chemistry of the interstellar medium directly to the formation of planets and the potential for life in the cosmos. Water ice coats the dust grains in every cold molecular cloud, yet spotting the same molecule as a gas has proven surprisingly difficult. When astronomers aim their telescopes at the dark hearts of star-forming regions, expecting to see abundant water vapor, they often find only a faint whisper of signal. This is the puzzle of interstellar water and oxygen, and it has deepened with every new observation. Water is one of the simplest and most widespread molecules in the universe. In the cold, dense cores where stars are born, water accumulates on the surfaces of dust grains, building thick icy mantles that can outmass the grain itself. We see this ice directly in infrared spectra, where it produces broad absorption features, so the ice is definitely there, locked away in frozen form. Yet when we search for water in the gas phase, in places where ice might evaporate, such as near young stars or in the diffuse interstellar medium, the signals are much weaker than models predict. Something is keeping that water frozen or destroying it as soon as it turns to vapor. The same mystery applies to oxygen, the element that combines with hydrogen to make water. Oxygen is the third most abundant element in the universe, and we should be able to detect it in its atomic and molecular forms throughout the interstellar medium. But the spectral lines of atomic oxygen are surprisingly faint, and the expected emission from molecular oxygen has proven almost impossible to find. This is known as the missing oxygen problem. Where is all the oxygen? Some of it is locked up in water ice, of course, but even with that accounted for, a large fraction remains unaccounted for. It may be hiding in refractory dust grains, bound up in silicates and oxides that are hard to observe, or it may exist in a form we have not yet learned to detect, such as in complex organic molecules that mix carbon and oxygen together. The situation becomes even more puzzling when you consider the role of water in star formation. Water is an incredibly effective coolant. When a molecular cloud begins to collapse under gravity, the gas heats up. If it cannot cool, the pressure from the heat would halt the collapse and no star would form. Water molecules, with their many rotational and vibrational transitions, can radiate away that heat at infrared wavelengths, allowing the cloud to shrink further. This makes water a key regulator of star formation rates. But if the water is mostly frozen onto grains, it cannot act as a coolant in the gas. So a cloud with a lot of ice but little vapor might collapse much more slowly than models predict. Observations from the Herschel Space Observatory, which operated from 2009 to 2013, were specifically designed to study water in the interstellar medium. Herschel's sensitive infrared detectors mapped water vapor across many star-forming regions, and the results were a shock. The amount of gas phase water was far lower than expected, often only a few % of what models had predicted. Even in regions where ice should have been evaporating, the vapor was missing. At the same time, the Airborne Observatory SOFIA, a telescope mounted on a modified Boeing 747, peered into the far infrared to study oxygen lines. It found that atomic oxygen, the so-called forbidden line at 63 microns, was present but often fainter than anticipated. The two mysteries, the missing water vapor and the missing oxygen, appear to be related. The leading idea is that water molecules that do evaporate from grains are quickly destroyed by ultraviolet light from nearby stars, breaking them apart into hydrogen and oxygen atoms. Those atoms then recombine into other molecules, or they may stick back onto grains and form ice again. This creates a rapid cycle of formation and destruction that keeps the gas phase abundance low. But the models have trouble reproducing the observed ratios, suggesting that some key chemical pathways are missing. Another possibility is that the oxygen is actually hiding in another molecule entirely. Carbon monoxide is the second most abundant molecule after hydrogen, and it contains 1 atom of oxygen for every 1 of carbon. If the carbon-to-oxygen ratio is high, then most of the available oxygen is already tied up in carbon monoxide, leaving little for water. But observations of carbon monoxide are well known, and they do not seem to account for the deficit, so the missing oxygen remains one of the most stubborn puzzles in astrochemistry. This mystery has a direct, intimate connection to the origins of planetary systems and life. Every water molecule that will one day fill an ocean on a planet like Earth must first form in interstellar space. Understanding the efficiency of that formation and the conditions that allow water to survive the journey into a protoplanetary disk is essential to understanding why Earth is a water world. And that understanding hinges on solving the puzzle of the missing interstellar reservoirs. As we dig deeper, we find that the story of water is tangled up with another element, deuterium, a heavier cousin of hydrogen. The ratio of deuterium to normal hydrogen in water molecules varies depending on the temperature and the chemical environment in which the water formed. By measuring that ratio, astronomers can trace the history of water, revealing whether it came from a cold molecular cloud, from a warm inner disk, or from a comet that later delivered it to a young planet. This is the mystery of deuterium fractionation, and it offers a way to link the interstellar chemistry of water directly to the formation of solar systems like our own. The clues are written in the subtle isotopic signatures of the water molecule itself, waiting to be decoded. A single atom holds the key to the entire history of the universe's matter. That atom is deuterium, a heavier cousin of ordinary hydrogen with an extra neutron in its nucleus. Deuterium is incredibly fragile. It was forged in the first few minutes after the Big Bang, during a brief window when the universe was hot and dense enough to fuse protons and neutrons together, but not so hot that everything broke apart again. Only a tiny amount of deuterium was made, and it has never been created in any significant quantity since inside stars. When a star forms, any deuterium it contains is quickly destroyed, fused into helium within the star's core. So every deuterium atom we see in the interstellar medium today is a fossil from the dawn of time, a direct relic of the Big Bang. That makes it one of the most powerful tools we have for measuring the density of ordinary matter in the universe. By measuring the abundance of deuterium relative to normal hydrogen, cosmologists can infer how much baryonic matter existed at the moment of primordial nucleosynthesis, and that number matches beautifully with what we observe in the cosmic microwave background. But when astronomers turn their telescopes to different regions of our own galaxy, they find something puzzling. The deuterium abundance is not constant. Along some lines of sight through the diffuse gas between stars, the ratio of deuterium to hydrogen is lower than the primordial value. In other directions, it is higher. The variations are not random. They seem to correlate with the amount of dust along the line of sight and with the local history of star formation. The leading explanation is astration, a term astronomers use for the destruction of deuterium inside stars. As generations of stars live and die, they consume the deuterium they are born with, while the rest of the interstellar medium gets diluted with the ashes of those stars. Over billions of years, the overall abundance of deuterium in the galaxy should slowly decline, but the rate of that decline depends on the efficiency of mixing. If the interstellar medium were perfectly mixed, the deuterium abundance would be uniform everywhere. Instead, we see patches of low deuterium, suggesting that some regions have been more heavily processed by stellar activity, while others retain a larger fraction of the original cosmic signature. Another possibility is that deuterium is being selectively destroyed or depleted onto dust grains. Laboratory experiments and theoretical models suggest that deuterium can stick more readily to the surfaces of cold dust grains than ordinary hydrogen does, because the extra mass makes it move a little slower. Over millions of years, this preferential depletion could remove deuterium from the gas phase, hiding it in the icy mantles of grains. If that is the case, then the observed variations might not reflect true destruction in stars, but rather a temporary trapping of deuterium onto dust. The debate between these two interpretations, astration versus depletion, has simmered for decades. Each new measurement from telescopes like the Hubble Space Telescope or the Far Ultraviolet Spectroscopic Explorer brings more data, but the pattern remains complex. Some regions show a clear correlation between deuterium and the amount of dust, supporting the depletion idea. Other regions show a correlation with the density of neutral hydrogen, which would be expected if astration were the dominant effect. The truth may be a combination of both, and the exact balance varies from one line of sight to another. This mystery matters because the primordial deuterium abundance is a fundamental anchor for cosmology. If we cannot accurately measure how much deuterium has been lost inside the galaxy, we cannot be sure that our estimate of the universe's baryon density is correct. It is a vital cross-check, and beyond cosmology, deuterium is a tracer of the entire life cycle of the interstellar medium. The way it is destroyed, preserved, and mixed tells us how gas moves, how stars form, and how galaxies evolve. Every time a deuterium atom is locked into a grain or fused inside a star, it records a chapter of that story. Deciphering the pattern is like reading the diary of the galaxy's chemical history. And as we try to make sense of these subtle isotopic clues, we are drawn inevitably into an even more fundamental puzzle. The same forces that govern the behavior of deuterium, the balance between ionization, chemical reactions, and the harsh ultraviolet light of nearby stars also control the basic state of the gas itself. How much of that gas is ionized versus neutral, and how that ionization is maintained, is a question that touches every part of the interstellar medium, from the coldest cloud to the hottest bubble. The ionization puzzle is the next secret the space between stars is ready to reveal. The same forces that govern deuterium also shape the ionization of the entire interstellar medium. Across the vast spaces between stars, a delicate balance determines how much of the gas is electrically charged and how much remains neutral. This balance is struck by a constant interplay of light, particles, and magnetic fields. Yet the exact pattern of ionization across the galaxy remains one of its most perplexing secrets. The primary sources of ionization are obvious enough. Hot, massive stars pour out ultraviolet photons energetic enough to strip electrons from hydrogen atoms. Each such star creates a bubble of ionized gas around itself, an HI region where the gas glows brightly in visible light. Supernova remnants also contribute as shock waves heat gas to millions of degrees, tearing atoms apart. Cosmic rays, those high-speed particles zipping through space, can knock electrons loose from atoms even in the cold, dense clouds far from any star. And diffuse X-rays from the hot interstellar medium provide a background bath of ionization that affects even the most remote pockets of gas. But when astronomers try to map the full ionization structure, they find a puzzling gap. Around young, massive stars, the HI regions are well-defined, sharp-edged bubbles of fully ionized gas. Yet beyond those bubbles, the diffuse warm ionized medium extends much farther than the number of observed ionizing photons should allow. Calculations show that the ultraviolet light from known hot stars cannot travel far enough to explain the widespread ionization we see. Something must be bridging that gap, allowing photons to escape the dense HI regions and travel great distances through the galaxy. The leading idea is that the interstellar medium is not uniform but porous, full of channels and low-density cavities carved by supernova and stellar winds. Ionizing photons can stream through these tunnels, reaching gas far from their birth stars, but the exact geometry of these escape routes is unknown. Different models produce wildly different results, and observations have not yet resolved the structure with enough detail to confirm or rule out the idea. This mystery of the ionization gap is tied directly to the larger question of pressure equilibrium in the interstellar medium. The gas in different phases, the cold neutral clouds, the warm ionized medium, the hot coronal gas, all exert pressure. For the interstellar medium to be stable over long periods, those pressures must roughly balance. But measurements show that the pressure in the warm ionized medium is often higher than in the surrounding neutral gas, suggesting that something is driving it out of equilibrium. That something could be the very photons that escape HI regions, heating the diffuse gas and puffing it up, or it could be turbulence and magnetic fields which add an extra component to the pressure budget. Until we map the ionization structure more completely, our understanding of how these phases coexist and interact will remain incomplete. And that missing piece is crucial because the pressure balance controls how gas moves, how clouds form, and how the galaxy breathes. Every photon that slips through the porous medium carries with it a clue to this hidden architecture, a hint of the vast, unseen scaffolding that holds the space between stars together. The coldest clouds and the hottest plasma sit side by side, yet their pressures are nearly equal. This is one of the most counterintuitive facts about the interstellar medium. Think about it. In the same patch of space, you can find a dense molecular cloud at just a few degrees above absolute zero, and right next to it, a million-degree bubble of gas from a supernova. The cloud has 1 billion particles crammed into every cubic meter. The bubble has only a few thousand particles in the same volume. their thermal pressures, the force exerted by the random motion of their particles, should be wildly different. But they are not. They are comparable, often within a factor of 2 or 3. How does this balance survive? The answer is that thermal pressure is not the only player. Magnetic fields thread through both regions, adding their own push. In the cold cloud, the magnetic field can be relatively strong, hundreds of microgauss, and it exerts a pressure that supports the cloud against the hot bubble pressing in from outside. In the hot bubble, the magnetic field is weaker, but the field lines are stretched and tangled by the turbulence of the explosion, contributing an additional component. Cosmic rays also add pressure. Those high-energy particles zip through both phases, and because they move at nearly the speed of light, they exert a force that is independent of the gas density. In the hot bubble, cosmic rays can be a significant fraction of the total pressure. In the cold cloud, they are less important but still present. Then there is turbulent pressure. The chaotic, swirling motions of the gas act like an extra force, pushing outward against the surrounding material. In the cold cloud, turbulence can be supersonic, rattling the gas at speeds faster than sound, and its pressure can rival the thermal pressure. In the hot bubble, the turbulence is subsonic but still contributes. So the interstellar medium maintains its pressure balance through a combination of thermal, magnetic, cosmic ray, and turbulent pressures, each one waxing and waning depending on the local conditions. But this explanation leaves a deep mystery unsolved. Why is the interstellar medium not dominated by a single phase? If pressure balance is so delicate, why does the gas not simply settle into one comfortable state, either all cold or all hot? The answer lies in the constant injection of energy. Supernova explode, heating gas and creating hot bubbles. Stellar winds push and compress the cold gas. Giant molecular clouds collapse and form new stars, releasing radiation that heats the surrounding material. The interstellar medium is kept forever off balance, churning between phases. It is a system that has no equilibrium, only a dynamic, chaotic dance, and the energy that drives this dance must eventually go somewhere. It dissipates. It turns into heat. That heat then radiates away, cooling the gas and allowing it to condense again. The puzzle of how that dissipation happens, how the turbulent energy of the interstellar medium is ultimately turned into warmth, is the next secret waiting to be uncovered. That turbulent energy does not simply fade away into the void. It has to be converted into something else, and that something is heat. But the problem is that supersonic turbulence, the kind that rattles through molecular clouds at speeds faster than sound, should dissipate its energy within a few sound crossing times. That is the time it takes for a sound wave to travel across the cloud. For a typical molecular cloud dozens of light years across, that timescale is only a few 100,000 years. Yet we know that molecular clouds survive for millions of years, and the interstellar medium as a whole remains turbulent over the entire lifetime of the galaxy. So there is a glaring mismatch. Something must be continuously pumping energy into the turbulence, keeping the cosmic storm alive. The obvious candidate is the same engine we have already encountered: supernova explosions. Each supernova injects an enormous amount of kinetic energy into the surrounding gas, stirring it up and driving shocks that propagate for tens of light years. If you could stand at the edge of a supernova remnant, you would feel the blast wave rattle every grain of dust and every atom in its path. Over the course of 1,000,000 years, dozens of supernova go off in a typical region, each one adding another jolt to the turbulent bath. But is that enough? When astronomers calculate the total energy budget, they find that supernova can indeed supply enough energy to maintain the observed level of turbulence in the diffuse interstellar medium. The catch is that the coupling between the explosion and the gas is highly inefficient. Most of the energy from a supernova is radiated away before it can stir the gas. Only a small fraction, perhaps 10% or less, actually goes into driving turbulent motions, and that fraction depends on the density of the surrounding gas and the magnetic field strength. both of which are poorly constrained. So the question becomes, are supernova really the primary driver, or do stellar winds, the steady streams of particles from massive stars, play a bigger role than we think? Observations show that regions with many massive stars are far more turbulent than quiet areas, which points toward stellar feedback as a dominant source. But the exact partition between different feedback mechanisms is still unknown. The mystery deepens when you look at the cold, dense molecular clouds, the very places where stars are born. In those clouds, the turbulence is supersonic, meaning the gas is churning at speeds many times the local speed of sound. That should create powerful shock waves that rapidly convert kinetic energy into heat. And indeed, those shocks do heat the gas, but the gas cools just as quickly, radiating the heat away in infrared lines, especially from molecules like carbon monoxide and water. So the dissipation is efficient, yet the turbulence persists. Something must be constantly injecting fresh energy to replace what is lost. The leading idea is that the energy comes from the gravitational collapse of the cloud itself. As a cloud collapses under its own weight, the gravitational potential energy is converted into kinetic energy, feeding the turbulence. This is a self-regulating cycle. The collapse drives turbulence, and the turbulence provides support against further collapse, slowing the star formation rate. But the exact balance between collapse, turbulence, and dissipation is delicate and hard to model. There is another candidate that is even more exotic: magnetic reconnection. This is a process that occurs when magnetic field lines of opposite direction are forced together, snapping and releasing stored magnetic energy. On the Sun, magnetic reconnection powers solar flares and coronal mass ejections. In the interstellar medium, it could happen wherever turbulent motions twist and tangle the magnetic field. When two field lines reconnect, they dump energy into the surrounding gas, heating it and driving small-scale motions. The efficiency of this process in the diffuse interstellar medium is almost completely unknown. Measurements of the magnetic field structure are too coarse to reveal the knotty tangles where reconnection might occur. Yet some theories suggest that magnetic reconnection could be a significant source of turbulent heating, perhaps even rivaling supernova. The combination of all these energy sources, supernova, stellar winds, gravitational collapse, and magnetic reconnection, is what keeps the interstellar medium perpetually churning. But the relative importance of each mechanism varies wildly from one region to another. In the hot, diffuse gas between spiral arms, supernova dominate. In the cold, dense cores of molecular clouds, gravitational collapse and magnetic reconnection may play larger roles. In the giant shells and bubbles carved by star clusters, stellar winds are the primary agitators. The result is a patchwork of turbulence with different flavors and intensities across the galaxy, and this patchwork leads directly into the next mystery. When we zoom in from the scale of entire clouds down to the scale of individual star-forming cores, the nature of the turbulence changes. At those tiny scales, the motions become subsonic, slower than the speed of sound, and the dissipation mechanisms shift. Understanding how turbulence transfers energy across these scales, from the grand swirl of a galactic spiral arm down to the gentle eddies around a newborn star, is the key to unlocking the fine-grained structure of the interstellar medium. That structure, the arrangement of gas and dust at resolutions smaller than a light year, holds the final secrets of how stars are born and how galaxies evolve from the inside out. At the smallest scales of the interstellar medium, a surprise was waiting that no one predicted. For decades, astronomers assumed that molecular clouds and atomic gas would fragment into structures no smaller than a light year or so, because that is the scale where gravity and magnetic fields usually set the limit. Then, in the late 1990s, observations using radio telescopes began to reveal something completely unexpected. Tiny, compact clumps of neutral hydrogen, barely a few hundred astronomical units across. That is roughly 10 times the size of our own solar system, an incredibly small patch of space for a cloud of gas. These became known as tiny-scale atomic structures, or TARS. And soon after, astronomers found their molecular counterparts, tiny-scale molecular structures, equally compact and dense, drifting through the diffuse gas between larger clouds. The mystery is not just that they exist, but that they should not be able to survive. Such a small clump of gas with a mass only a tiny fraction of Earth's would normally be torn apart by the surrounding pressure and the gentle tidal forces of the galaxy. It should evaporate in a few thousand years, vanishing back into the thin, warm medium around it. Yet we see them, they persist. Something is holding them together, protecting them from dissolution. The leading idea is that these tiny structures are protected by magnetic fields. Inside each clump, the magnetic field might be unusually strong, creating a sort of magnetic cocoon that resists the outside pressure and prevents the gas from expanding. Alternatively, they could be stabilized by a small amount of dust that shields the gas from ultraviolet light, keeping it cold and dense. But the survival problem is not the only puzzle. How did these structures form in the first place? They are far smaller than any turbulent eddy or gravitational fragment should produce. Some researchers suspect they are the remnants of larger clouds that have been shredded by stellar feedback, leaving behind dense cores that have not yet had time to dissipate. Others think they might be formed directly by the compressive action of fast shocks, focusing gas into tiny, dense knots that cool rapidly. There is even a daring idea that these could be the seeds of future planets, tiny concentrations of gas and dust that later accumulate into larger bodies. If that is true, then the search for extrasolar planets might have a direct link to these elusive interstellar specks. The implications for star formation are also profound. If such small structures are common, then the process of forming stars must be influenced by clumps that are far smaller than we ever accounted for. They could provide the initial density fluctuations that grow into protostellar cores, or they might represent a previously unknown pathway for building very low-mass stars or even brown dwarfs. Every new observation of these tiny clumps, using arrays of radio telescopes that can resolve details as fine as a few astronomical units, adds to the picture, but the picture remains fragmented. These structures are hard to find because they are small and faint. Only a handful have been studied in detail, and we do not know how many exist across the galaxy. Are they rare anomalies or a common feature of the interstellar medium? The answer could reshape our understanding of gas dynamics at the smallest scales. And that brings us to the 30th and final mystery in this journey through the space between stars. This last puzzle pulls together everything we have explored, from magnetic fields and turbulence to chemistry and star formation, and asks a question that touches the very origin of our own solar system. Dark matter is the unseen skeleton that holds galaxies together. You cannot see it, touch it, or detect it directly with any telescope, yet its gravitational pull dominates the motion of stars and gas across the entire Milky Way. Every atom of the interstellar medium that we have been exploring, every molecule, every dust grain, every wisp of hot plasma, is moving inside a gravitational well shaped primarily by this invisible substance. And that simple fact leads to one of the most profound and least understood mysteries of the space between stars. The total mass of dark matter in a galaxy like ours is roughly 10 times the mass of all the stars and gas combined. Its distribution forms a vast, diffuse halo that extends far beyond the visible disk. This halo creates a gravitational potential, a kind of deep dish in space that pulls everything toward the galactic center. The gas of the interstellar medium, whether it is cold hydrogen or hot supernova ejecta, must orbit and flow within that potential. If the dark matter were not there, the gas would simply drift apart or fall far more slowly into the disk. The very existence of a thin, stable galactic disk, where stars and molecular clouds can persist for billions of years, depends on the gravitational anchor provided by dark matter. Yet the influence is not just a simple pulling inward. The shape of the dark matter halo, whether it is perfectly spherical or slightly flattened, affects the rotation curve of the galaxy, which in turn sets the shear and turbulence that we measured earlier. A slightly lopsided halo can create torques that drive gas toward the center or push it outward, altering the star formation rate across the entire disk. Simulations that try to include the full structure of dark matter, including the clumps and streams predicted by models of cold dark matter, reveal that these substructures can tug on the interstellar medium in subtle ways. They can stir up the gas, create density waves, and even trigger the collapse of molecular clouds in regions far from any visible stellar feedback. The problem is that we have never observed these dark matter clumps directly. We see their gravitational effects on the orbits of stars and the shapes of galaxies, but we cannot see them interact with the gas in any other way. That raises the central unresolved question: does dark matter interact with ordinary matter only through gravity, or is there some additional, faint interaction that we have not yet detected? Some theories propose that dark matter particles could occasionally collide with atoms in the interstellar medium, releasing a tiny flash of energy or a faint glow that we might be able to observe. Experiments like those deep underground searching for dark matter particles have not found any convincing signal, but the diffuse gas of the ISM offers a completely different laboratory. If dark matter can scatter off nuclei in the gas, it might heat the gas in specific ways or produce excess cosmic rays that we could trace back to their source. The absence of any observed signature so far only deepens the mystery. The interstellar medium, with all its complexity, is therefore not just a collection of gas and dust. It is a detector for the invisible universe. Every measurement of a cloud's motion, every map of a galactic rotation curve, every observation of a dwarf galaxy's gas content carries information about the dark matter that surrounds it. And yet we have only begun to read that information. The final mystery of the interstellar medium is that it sits at the crossroads of astronomy, cosmology, and fundamental physics. It is a place where the ordinary matter we can touch meets the dark matter we can only infer. Every unanswered question we have explored, from the formation of hydrogen molecules to the survival of tiny atomic structures, is ultimately connected to the gravitational stage set by this invisible hand. The space between stars remains a frontier, not just for understanding the birth of stars and planets, but for uncovering the very nature of the universe's dominant ingredient. And that is why, after 30 mysteries, the story of the interstellar medium is far from over. It is just beginning a new chapter. These 30 mysteries barely scratch the surface of what we have yet to learn. From the uncertain composition of interstellar dust to the invisible hand of dark matter shaping the gas flows, each unsolved puzzle is not a dead end but a doorway. Together they reveal that the interstellar medium is far more than a passive backdrop. It is an active, dynamic system where the fate of galaxies is decided, where the raw materials for planets and life are assembled, and where the fundamental forces of the universe compete and cooperate on scales from atoms to light years. The very fact that we still do not know what makes up most of the matter between stars, or why star formation is so inefficient, or how magnetic fields truly control the gas, is a testament to how much remains to be discovered. Every time a new telescope comes online, whether it is the James Webb Space Telescope peering into the infrared heart of a molecular cloud, or the next generation of radio arrays mapping the faint glow of the cosmic web, we get a little closer to lifting the veil. The coming years promise to be a golden age for interstellar research, with missions designed to measure the missing baryons, to identify the carriers of the diffuse interstellar bands, and to trace the cycling of gas from the galactic disk to the halo and back again. For the viewer who has joined us on this journey across 30 mysteries, the invitation is simple: keep watching the skies, keep following the discoveries. And if one of these puzzles has captured your imagination, share it in the comments below. What part of the interstellar medium do you find most mysterious? Is it the ghostly diffuse bands, the missing baryons, or the dance of turbulence and magnetic fields? Subscribe to stay updated as we continue to explore the hidden universe, and in our next video we will dive into the secrets of the cosmic web, the vast network of filaments that connects galaxies across the void. Until then, remember that the space between stars is not empty, it is alive with questions waiting for answers.